Hello, folks. So, dynamic programming is one of the most important topics in any technical interview. On top of that, it is one of the foundational concepts of problem solving and data structure and algorithm. So many companies and so many products are actually built on the core concepts of dynamic programming. So, in my personal opinion, it's not only about learning the dynamic programming, but rather than actually understanding that how to come up with that solution and how does it saves up on your computation power. In this video, I'm going to show you top 10 most asked technical interviews for the dynamic programming, and these have been widely accepted throughout all the top companies. And you can go and check them out, like what are the companies have asked them on lead code and stuff like that. The purpose of this video is to give you more practice. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. The problem we are going to do today is actually asked in a lot of top tier IT companies, and if we look at the recent data, it has been asked in Amazon 20 times, Apple 8 times, Facebook 2 times, Google 6 times. So needless to say that this is a really important problem. So I hope you provide your utmost attention. This is the outline on how we are going to solve this and the things I'm going to cover in this video. So first we'll understand the problem statement. I will be creating a brute force solution. Then we will build an optimal solution with dynamic programming. And at the end, I'm going to show the Java code for this one. This is a lead code medium problem, but in my opinion, it should be a lead code easy problem because it's not very difficult to understand. But the thing is, its concept is really important. That helps you build the conceptual knowledge of dynamic programming, which you can use in bunch of different problems. And a lot of FAANG companies loves to ask this kind of questions. So if we understand the problem statement, basically we are a professional robber and we are planning to rob houses in each street. Now the thing is, the way houses are mentioned in the street is that every single house has some amount uh, in that particular house. But the only condition we have is if we rob one house, we cannot rob the house that is exactly adjacent to it. So suppose we decide to rob this house. If we rob this house, which means that we cannot rob this house or this house, and we can again, if we want, we can again rob this one. So that option we have, and the our aim is to maximize our profit. So basically we are given an input array nums that shows that for every single house how much amount of money is presented over there, and we need to see that what route can we take which maximizes our input or the amount of money we can steal, and we need to show that in the output. So let's try to understand this with an example. So basically over here we are given the values as 1, 2, 3 and 1. So notice that the maximum amount we can steal is basically if we go down this path. So if we start with the first house and then notice, then we can't rob the second house, but then we rob the third house, and the sum of these two would actually become 4, and this would be our answer. So for the brute force, we are going to solve the same problem. Basically, one way to understand the brute force approach is that at every single position, initially we are at 0th location. So if we just make all the possible pairs which we can create where we can rob houses, basically that would be our solution. So let me show you how. So initially at 0th position, now we have two options. Either we can select the value number 1 or 2. So either we can select the first value or second value, and these are the subsequent values. Now at this position 1, we again have two options. Either we can rob the third house from here, or we can skip the third house and we can also rob the fourth house if we want. So the two choices we have over here is either we go down this path or we go down this path. And at this house number 2, we only have one option. We can't rob this 1 or we can't rob this 3, so we can only rob this 1. So the only choice over here we have is actually 1. And now we just do the sum of all the values. So for this path, the sum we would get is 4. For this particular path, the sum we would get is 2. I just put it in a box so it's easier to differentiate. And down this path, the maximum sum we can achieve is 3. So if we compare these three elements, we can clearly see that 4 is maximum, so we simply return 4. Now brute force solution works, but the problem with this one is that we need to create every single pair, and in order to generate pair, essentially at every single position we have two options, that whether we need to keep this value or we do not need to keep that value, and that eventually would bring a lot of different values in our graph and on the number of decisions we can make, which means that the time complexity for brute force approach would be, you guessed it correctly, 2 to the power of n, where n is basically whatever the number of inputs given over here. And you guessed it correctly. Also, I already gave it away, but we are going to use dynamic programming over here, and let me show you how we can use dynamic programming to solve this problem. We are going to use a custom example, and I have already mentioned it a bunch of times that it is really important to have your own custom examples. That shows that you can think outside of the box. So over here initially, we are at this position, value number 2. Okay, so what we can determine is that initially at this position, if we were given only one house, what is the maximum amount of value we can steal from this particular house? Of course, the answer is pretty simple. We can only steal whatever we are given, right? Because we are only given just one house. So initially at this point, suppose if we create an additional data structure that keeps the track of what is the maximum amount of money we can steal up for any element, then our decision making will become easier, and we would be able to choose that what path we want to take. So let me show you by an example. So initially at this position, value number 2, the maximum amount we can rob will only going to be 2, because there are no other values before that. So this is the maximum amount we can rob so far. Okay, now this at value number 4, the maximum amount we can rob is actually, up until this point, it's only 4, because we can't use 2 when we are robbing 4. If we choose to rob this second house, if we choose to rob this one, we can't use it. We can't basically use this first house. So we know that for the first two values, these are the maximum amounts we can rob. Now we are at this position number 3. So at this position number 3, we have two options. Choices are pretty simple. Either whatever the value maximum we have so far over here, which means that so far the maximum value we have is 4, or whatever the previous maximum value we had plus whatever value we currently are at. Because remember, if we decide to rob this house number 3, basically we still have the option to rob house number 2. We can't rob house number 4. So up until this value number 5, the maximum we can rob so far is actually 5. Why? Because we check that, okay, up until this point, what is the maximum that previous element has robbed? Basically, like one house before this house has robbed, and that maximum value is 2. So I can do 2 plus 3. So maximum I can rob up until this point is actually 5. So okay, we have this knowledge, and up until this value, the maximum we can rob is 4. Now let's forget about this one for now, because anyways at any given time we are only concerned with the house that are adjacent to each other. Now we are at this position number 9. So what is the maximum value we can rob up until this point 9? Well, the answer is quite simple. We check that, okay, what are the two values before this 9? So this is 5, which means that if we decide not to rob this house, the maximum we have robbed so far in this sub array is actually 5. But how do we decide that whether we want to keep this 9 or not? Well, we just need to apply the same logic. The house that is adjacent to 9, before that, what is the maximum amount we have found? So the maximum for that is 4, and we do 4 plus 9. So 4 plus 9 is 13, which means that up until this point, the maximum we can get, the amount is 13, which is definitely greater than 5. So it is in our interest to keep this pair so far. Now we can forget about this 4 because we already calculated its value over here. And now at this next value, value number 11, again we have two choices. Do we want to keep 11 or not? So again we do the same thing. We compare 11 with whatever value we have over here. We do, first of all, we do sum of 11 plus this 5. So we do 11 plus 5. Okay, this one is 16. So which is greater than 13, which means it is in our interest to keep the value 11. So again we are going to have 16 over here. We can forget about this one because we already calculated its value. And yeah, so we are at, now the two choices we have is 16 and 13, and this value number 2, we need to check two items. So value before that, this is 16 and this one is 13. So we do 13 plus 2, 15. So far, if we decide to keep this value number 2 in our list of houses that we are planning to rob, the maximum value we can achieve so far is 15. But the thing is, we have already found a better option than this 15, and which is 16, where if we decide to rob these three houses, we will get the optimal answer. And notice that we were able to complete this whole iteration in just single we were able to complete this whole calculation in just a single loop, because we were keeping track of whatever the elements we have calculated so far, which is the exact use of dynamic programming. And we are not using more than one element at any given moment, which means that our solution is actually quite helpful and very perfect. So let's calculate the time and space complexity, and basically this would be the optimal solution. So time complexity, as you have guessed it correctly, it's actually big O of n, because we are completing everything in just one single iteration. We don't need to do multiple rounds of checks. And the space complexity we have is actually big O of 1. It's actually constant time, because notice that at any given moment, the maximum value we were keeping track of is just couple of elements. And we kept on updating our elements, that whatever we were keeping track of, which means that we are not using that much space. We are not creating an additional array to store all the values. Okay, let's create two elements. We'll name it rob1 and initialize it to 0, and we'll create a rob2. We'll also initialize it to 0, and we'll have another variable. We'll just name it max to keep track of maximum element that we have calculated so far. And now let's run a for loop. Inside the loop, first of all, we'll calculate that whether we have achieved the maximum value or not. So max would be whatever value we have at rob1 plus whatever value we are currently at. So this is one option, or whatever the value of rob2 we have, because notice that the rob2 element is actually right adjacent to this ith element. And now we need to update the values of rob1 and rob2. So rob1 will actually become whatever value of rob2 we had, because we are updating it every single iteration. And rob2 will actually become the maximum value we have found so far. And yeah, I think this should be our solution. And at the end, we will return the max element. So let's try to run this code. Okay, our solution seems to be working. Let's try to submit it. Oh, okay. Yeah, our solution is actually runs in 0 millisecond, and it's 100 times faster than all the other solutions. But the thing is, this is not true. because we are given a limited number of test cases, we are computing everything in just constant time, so that's why it's showing us 100% faster. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do a very important problem, House Robber 2, and this is actually an extension of original House Robber problem. I have already solved the House Robber problem over here, so you can check out that video, and I highly recommend that you check out that video before coming on to this problem. Typically in any interview, this problem is actually going to be asked as a follow-up question after they have originally asked this house robber problem. And that is why if we see the number of companies that have asked this question recently, it's actually quite small compared to what we are used to seeing for the other companies. But the thing is, still Amazon and Google have asked this recently, even Microsoft asked this just a little bit sometimes back, and also a few other companies have asked this. So this is a lead code medium problem, and basically the problem statement is saying that we are professional robber and we are planning to rob houses along a street. Now the catch over here is that all the houses in this given street are actually arranged in a circular fashion, and also there is one more constraint, that we cannot rob two houses that are adjacent to each other. If we rob two houses that are adjacent to each other, basically police is going to be called and we will be caught. So this is a constraint that we have to look into, and our motive is to collect or gain or rob as much money as possible without being caught. So let's try to see a pictorial representation. So basically all the houses in the street are actually placed like this. So suppose if we consider that this is our first house, actually the first house is also neighbor of the last house in the given street, because all the houses are stored in a circular fashion. And now since the houses are stored in a circular fashion, that is one more thing that we need to consider. And also we cannot rob two adjacent houses. So suppose if we decide to rob this house, we cannot rob this house or we cannot rob this house. So the first example we are given is the houses are placed like this, and these are the amount of money that is at each house. So basically, since there are only three houses, we can only rob one house, and we need to select the house with maximum money. So it's pretty simple over here, that if we select this house, we get the maximum money, and if we rob the house with value number 3, we can't rob these two houses because they are adjacent to each other. In the second example, the houses are stored like this: 1, 2, 3 and 1, and the most amount we can collect over here would be if we rob this house and this house. So in that case, the amount of money we would collect would be 4, and we won't be able to rob these two houses because they would be adjacent to each other. So we already know the brute force approach. Basically the brute force approach is to make every single pair and check out all the possibilities to see how we can find the answer. But the thing is, there is no point in exploring brute force approach over here. I'll directly go to the most optimal solution that we are going to achieve using dynamic programming, because this is an extension of House Robber 1. If you want to get more information about the approach, you can check out that video first. So for the optimal solution, we are going to use a custom example, and this is very important to use custom examples because it shows that you can create test cases on your own, and this is a really good skill to have in actual computer world. So suppose the number of houses we are given over here are in this fashion, and let's try to draw them in a circular manner. Now basically we can use the same solution we were using in House Robber 1, because remember in House Robber 1 what we were doing, we were just simply going through whatever the input we had, and we were just keeping track of what is at any location, what is the maximum amount of money we can rob up until this element by checking the previous values. We are essentially going to do the same thing over here, but just in a little bit different manner, because in the House Robber 1 problem we were considering the whole thing because they were all the houses were placed in a straight line, so we were able to consider them like that. The thing is, over here the additional constraint is that whatever the last amount or the last house is actually neighbor of the first house, which we can see over here that these two houses are neighbors of each other, which means that if we at any point decide to rob this house, we cannot rob this house, or vice versa, that if we decide to rob this house, first house, we need to make sure that we do not rob this house. So the answer is actually quite simple. Rather than treating this as a circular street, why don't we just run two functions? So basically, during the first loop, during the first iteration, we are going to check the first sub problem, and let me show you what I mean. The additional constraint we have over here is that if we consider this house, it is guaranteed that we cannot use the last house, or if we use the last house, it is guaranteed that we cannot use the first house. So since we know that this condition exists, we are simply going to do calculation twice. In the first calculation, we are going to check between these houses that what is the maximum amount we can rob, and during the second loop, we are going to check that amongst these houses what is the maximum amount we can rob, and then we just need to compare that what is the maximum value we have found across both the loops, and whatever the maximum value we find, we just we just submit it as our answer. So let's iterate over the entire problem. Okay, so these are the two loops that we are going to iterate over. So let's calculate the result for the first loop. So at the first position, the maximum amount we can rob so far is only going to be 1. And at the second house, the maximum amount we can rob is only going to be 2, because we cannot rob the first house. Now, for the third house, we have two options. Either we keep whatever the value of 2 we have, or we keep the value of 1 plus the third house value, and we see that whatever is the maximum value amongst these two, we are going to keep that. So 1 plus 15 is going to be 16, and of course 16 is greater than 2, so we are going to say that up until this house number 3, the maximum amount we can rob is 16. Now we are at the fourth position. Now over here, the maximum amount we can rob is actually 2. We have two options. Either we can rob on 16 units, or we can do 2 plus whatever value at house number 4 we have. So 2 plus 11 is actually 13, which is less than 16. So even up until this point, the maximum amount we can rob is still going to remain 16 and not 13, because definitely 16 is greater value, so it is in our interest to keep this value 16. Now again we are at this position 3, and also notice that at any given location we are only considered with values that are of previous two houses that we have calculated over here. We don't need to consider all the values, because we are already adding them up and we are only keeping the maximum values. So this works in our favor. So at value number 3, the maximum we can achieve is either 16 plus 3 or 16 by itself, which is this 16 or 16 plus 3. So of course 16 plus 3 is going to be greater, so we are going to store 19, and we don't care about these values anymore because we already have the latest values so far. Now at value number 6, the maximum we can find is going to be 16 plus 6 or 19. We need to select whatever is greater. So 16 plus 6 is 22. This is the greater value, so we are going to keep this and we don't care about 19. So we can see that at the end of this first loop, the maximum value we have found so far for this particular set of houses is 22. Now let's repeat the same process for the second loop. So in the second loop, for the first position, the maximum we can rob so far is 2. At the second house, the maximum we can rob is 15. Now over here, the maximum we can rob is either 2 plus 11, which is 13, or 15. So of course 15 is greater, so we are going to keep 15 over here. Now at this position number 3, we can either do 15 plus 3 or compare it with 15. So 15 plus 3 is 18. So we are going to keep 18 over here. Now at this position, we consider these two values. So either we do 15 plus 6, which is 21, or we check with 18. So 21 is greater. So of course we are going to keep this one. And now at this last position, we check that whether 21 or 18 plus 10. So of course 18 plus 10 is 28. So we are going to keep that, and we do not consider about 18. So after this entire loop, the maximum value we have found so far is 28, and the maximum value we had found over here was 22. So our job is pretty simple. We just need to see that whichever value is actually greater, we simply return that. And in this case 28 is greater than 22, so 28 would be our answer, and we just return that value. This is a very good solution. We are building it on top of whatever we have solved for house robber 1, and because we are basically using the same solution, we are just changing the scope of up until what points we are using this solution. So just keep that in mind. And if we calculate the time and space complexity, the time complexity for this one is going to be big O of 2n, because we are running two loops, 0 to n minus 1 and 1 to n. So if we generically mention this, it actually becomes big O of n. And if we calculate the space complexity would be big O of 1, because we are, apart from storing couple of parameters, we are not using any additional space. So that's why we are able to run this in a constant time. Constant space. Okay, let's start creating parameters. So we are going to need two parameters, rob1 and rob2, and we are going to initialize both to 0. We will also need two parameters to store two maximum values, so we'll name them max1 and max2, and max1 will initialize it to the 0th house, and max2 we can actually initialize it to 0, because we are not going to consider the first house, and we are keeping the max1 as 0 because in case we are given the condition where we only have one input, so we can simply return that. Now let's run a for loop starting from the first house. So I equal to 0 to I is less than length minus 1, I plus plus. Okay, over here we are going to calculate max1. So max1 would be maximum value amongst rob1 plus the current number we are at, or the value of rob2. And we also need to update the value of rob1 and rob2. So rob1 would actually become rob2, and rob2 will become the maximum value we have found so far. Now once we are done with this loop, we need to reset the values of rob1 equal to 0 and rob2 equal to 0, because we are going to use them again in the second loop. And we are going to create another for loop, I equal to 1, and we are going to set up I is less than, so nums dot length I'll plus plus. Okay, and essentially we are going to use the same conditions. By the way, this would be max1. We are going to use the same condition, so we can just reuse the code, and we are going to, rather than calculating max1, we will be calculating max2. So let's do that. And after the second loop, we simply need to return whatever the maximum value we have found amongst max1 and max2. And this should be the solution. Now notice that I am running two loops over here, but the thing is, an efficient way to do this is to create a function, and function would intake the parameters like start and end value, and you can just repeat this process. So that would be an efficient way to do this code as well. Let's try to run this. Okay, seems like our solution is working. Let's try to submit the code. Today we are going to do a very important problem, climbing stairs. Though it's a lead code easy problem, everyone should do this problem because it gives you a really good introduction towards dynamic programming, and this is one of the core concepts that a lot of companies likes to ask. So let's understand the problem statement. We are climbing the staircase and it takes n steps to reach to the top, and every time we can either climb one or two steps, and we need to show that how many distinct or how many separate ways can we climb to the top. We are going to understand this problem with three examples. Suppose we are only given just one step and we need to climb that one step. So how many distinct ways we can climb that step? Only one, because we just take one step and we are already at the top. So there will be only one distinct ways we can climb to the top. Suppose we are given two distinct steps and we are trying to reach to the top. So this is our first step and this is our second step. The distinct ways are actually two. One way is we take first step at the first step and we take one step again. So this would be our first approach. And second way, we can directly take two steps, because remember, we can either take one or two steps. So if we directly take two steps, we will still reach at the top. So in this case, we can do it in two distinct ways. For the third example, suppose we are given three steps and we need to find that how many different ways we can climb that. Apologies on my painting. I'm not the Pablo Picasso of this generation for sure. The first way we can climb over here would be the most simple one, that we take one step each time to reach to the top. Second way would be to take two steps directly at the beginning and then take one more step. And the third way is that we take one step at the beginning and then we take two steps. Other than that, there are no other possible ways to reach to top apart from these three. So the total number of different ways we can reach to the top for the staircase number 3 is actually 3. And now that we understand that what we need to calculate, let's see what could be the different approaches. Our first intuition is that if we start at the step 0 and suppose our n is equal to 5 that we need to calculate, if we take the decision that at every single level we are either going to take one step or two steps, and then when we reach to number 5, we will calculate that how many distinct ways we took to reach to value number 5, and then all the combination of all those distinct ways would be the separate ways we can reach to 5. So that would be our answer, and this is the most primitive approach we can take. So let me show you how it would look. So at the beginning, at value number 0, we have two possibilities. We can either take one step or we can take two steps and we can reach to the second step. Suppose we only take one step, then again we have two possibilities. We can again take just one step and we will reach to 2, or we would take two steps to reach to the step number 3. Again same. So over here we will reach to 3 and over here we will reach to 4. And now over here we would reach to 4. But notice that at the 4, we only have one possibility. We can only take one step, because if we take two steps, we reach to 6, which is higher than our given input. So we can only take one step, and now we have reached to the final point that we can reach to. But at the 4, we still have, and even at the 3, we have possibility to reach at 4, or we can take two steps directly and we can reach to 5. So over here, again, we end our possibilities, but at value number 4, we would take one more step and we can reach to value number 5. Now, at this value 3, we still have two options. We can either take one step, we would reach to 4. Again, we take one step, we would reach to 5. Or we can take two steps directly and we can reach to 5. Now we have exhausted all the possibilities from 0 to left side of the subtree if we take the first step as 1. So now let's explore the possibilities on the right side. Notice that at all the elements where I have done the square, or number 5 shows a distinct way. So suppose for this one, the distinct way would be just to keep on taking one step each time. for this one, we are taking one step up until the third step, and then we are taking the two steps. So if we calculate all these values, the number of different ways we can do this is 1, 2, 3, 4, 5, 6, 7, and 8. So based on this, we can determine that there are 8 distinct ways we can take if we are given the n is equal to 5 and if we want to climb the 5-step stairs. So we can have a recursive function that at every location of n would call itself for I plus 1 and I plus 2 while I is less than or equal to n. And we would be able to reach out to this solution. But the issue with this solution is this is highly inefficient. And if we see over here, at any given node, we are making two decisions, and based on those two decisions we are again making two decisions down the line. So pretty soon, if our value of n goes high, we would be running out of the possibilities, and the time complexity for this approach is actually 2 to the power of n, where n are the number of nodes, or in this case number of stairs. But this is a pretty heavy time complexity and we should avoid it in all cases. So let's see that what are the better approaches we can take. The first approach we can take is actually to reuse the work that we have already calculated. If we see this graph, it becomes pretty evident that we are doing a lot of repetitive work every single time. Suppose if we just take this left side of the route and we have calculated the results up until this point, we know that whenever we are at value number 4, there is only one possible way to which we can reach to the top. And we are doing this work again and again and again at different locations. Again, same thing happens when we are at value number 3. If we are at value number 3, there are only two distinct possible ways we can reach to value number 5. So even when we are at value number 3, suppose we have calculated that over here when we are at value number 3, we only have two distinct ways to reach to value number 5. Why are we doing all of this repeated work over here, then again over here? This could be avoided, and same can be avoided for the work done at value number 2. We calculate towards this route and we calculate all the possibilities. So we know that from value number 4 there can only be one distinct route, from value number 3 there can only be two distinct route, and from value number 2 there can only be three distinct routes possible. So we can use this to our advantage. If we know that at value number 2 we can only have three possible different values, we can directly use that over here and we can get rid of all of these values, because we know that at value number 2, when we reach to the second step, there are only three distinct possible ways to reach 5. Again, same thing would apply over here, that at value number 3 we know that there are only two distinct ways we can reach to 5. So after the first step, whenever we reach at the third step, we can directly say that there are only two distinct possible ways we can reach to 5, and we won't have to do all the calculations. Same over here, whenever we reach at 4, we know that there is only one distinct route we can reach because we calculated it over here. So we can again get rid of this step. We will simply put it over here and we can just say that there is only one distinct ways we can reach. So using this, we are able to avoid lot of extra work that was being done. So let's see that what would be the approach for this solution would be, where we are storing all the results that have been previously calculated in some sort of an array, and we are going through the nodes. So notice that we are only going through the nodes once, and then whenever we encounter those nodes again, we are using whatever values we have stored beforehand and we are reusing that. So the amount of work being done is actually pretty small. And if we see the time complexity for this approach, the time complexity is actually big O of n, because in one single iteration we are able to determine all the distinct ways that we can reach to 5, and then we are just reusing those values at different positions in the given loop. And if we see the space complexity is also big O of n, because we will have to create some sort of data structure to store the values of all the distinct ways we can reach to 5 at any given location. If we consider this from our brute force approach, this is actually a much better improvement, but can we still get a better result? Suppose our given value n is equal to 4, we can represent it like this. And now let's try to understand the logic behind that. How can we calculate that how many number of different ways are there to reach 4? First, we have to determine that what are the direct elements or direct values from where we can directly jump to 4. So we know that we can either do one step jump or two step jumps. So from 3, if we do one step jump, we can directly come to 4. And from 2, if we do a two-step jump, we can directly come to 4. Now, this is a really important thing to consider. What this essentially is telling us that no matter how many different ways we can reach to this value 2, if somehow we can reach to this value 2, all of those ways would allow us to reach to value number 4 directly. So let me show you what I mean. So we know that there are two distinct ways to reach to 2. Our first way is we reach to 1, and then from 1 we reach to 2. And once we are at 2, we can directly go to 4. Now, second way to reach to 2 is that at the beginning we directly take 2 steps forward and we reach to 2. Once we are at 2, we can directly go to 4, and this would also be a distinct route. But in both the cases, the common thing is that we found out the number of times we were able to reach to 2, and in both of those cases we ended up at 4. Again, same thing occurs when we consider the value 3, that we know that from 3 we are just one step away to reach to 4. So basically all the routes that can lead up to us to reach to value number 3 can lead us to reach to value number 4. And let's take an example for that as well. So from the beginning we can go to 1, then we can go to 2, and then we can reach to 3, and that would lead us to 4. So this is one possible route. Second possible route is that we can directly go to 2, and then we can go to 3, and from 3 again we will be ending up at 4. We initially start at 1, so we take one jump, and then we take two jump to reach to 3. Then we would be able to reach to 4. So in both the cases, essentially once we are at the value either 2 or 3, we end up being on this value 4. So the moment we reach to element number 2 or element number 3, we can say that from there we can directly reach to element number 4, and we cannot go anywhere further from 4 because there does not exist any step over here. So we end at 4, and the number of distinct way we can reach to 4 would actually be the summation of the summation of number of different ways we can reach for value number 2 plus the number of different ways we can reach value number 3. So suppose we define that we need to calculate that how many distinct ways we can reach to 4, and this dw represents distinct ways to reach 4. We can calculate this as that distinct ways to that we can reach to value number 3 plus the distinct ways we can reach value number 2, and summation of these two values would lead us to the number of distinct ways we can reach to value number 4. And this is a really important property, and based on this we would be able to solve our dynamic programming solution. So let's clear this up a little bit. Basically in our algorithm we will keep track of two values, uh, value number one jump and two jump. So one step jump and two step jump, we will keep track of these two. and the initial value would be that for one step it would be 1, for two step it would be 2, and we can just put a condition that if the value of n is equal to 1, we would just simply return 1, because that would be our base case, and we can't go any further than that. And now we have the values for first element and second element. So we will start our loop, and in our loop we'll start it with value number 3 all the way up to n inclusive. The reason we are starting it at value number 3 is because we have already calculated the results for value number 1 and value number 2, as value number 1 would just be 1, and for value number 2 the number of possible ways we can find would be in this parameter 2 jump. Now inside the loop we will calculate this property. So we will simply do a total of whatever the value of 1 plus 2 we have. So we need to update the value for 1 and 2. In order to update the value of 1 and 2, we need to first understand that what value number 1 and 2 represents in our given example. So 1 represents the element, the position of that element from where we can, if we just take one jump, we can reach to our ith element. So if we are calculating that I is equal to 3 and we need to calculate the values of 1 and 2, 1 originally 1 would be here and 2 would be here, and now we will do a total, and total will give us the value for element number 3. Once we are done with this and once we are going for the next iteration, in the next iteration we will need to update the values so such that this 4 gets the value of 3 and 2. So 2 would be jumped over here, which means that 2 would receive the whatever the value of total we calculated of this 1 plus 2, and our value 1 would jump to this position, and it will take whatever the value of former 2 we had. So the new graph would become like, for value number 4, this would become the 2 and this would become the 1. And when we are inside the loop, we will do a total, and again we will repeat the same process, that we will jump our 1 over here and we will jump over 2 on this position. So we will get the whatever value of total we have, we will put it in the 2, and yeah, at the end of the loop we can return to. So over here we would define 1 is equal to whatever value of 2 we had, and 2 is equal to whatever value of total we have. And at the end of the loop, we will just simply return whatever the value of 2 we found as our result. And we can simply return 2 over here. Now let's calculate the time and space complexity for this approach. The time complexity, the time complexity would be big O of n, where n represents the number of steps that we are given. And for the space complexity, we can calculate in big O of 1 time, because other than storing couple of parameters, we are not using any additional space. So this would be a pretty efficient solution. There is also one more solution that provides the answer in actually log n time and also constant time, but the thing is those are pretty mathematical and they, in my opinion, does not serve the purpose of checking your computer related knowledge. So even in the interview, if we come up with this approach and if we show that we know dynamic programming, I think this would give us an edge over other candidates, and this would be sufficient for us to prove that yes, we are more familiar with computer science related concepts. And yeah, we might not be up to date on mathematical concepts, but this is not where what the FAANG companies are judging us on. Now let's move on to coding. Okay, so first of all, we are going to create a condition that if n is equal to 1, we will just simply return 1. And now let's define two parameters for one step and two steps. So we can say one step and we can initialize the value as 1, and we can say 2 we can create a variable for 2 steps, and we will initialize the value as 2. And now we will create a for loop, and we will create a for loop starting from the third position, because we already have the results for n is equal to 1 and n is equal to 2. Well, I is less than or equal to n, I plus plus. Inside the loop, first of all, we will just create a variable total to store the sum of 1 plus 2. And with every iteration, we need to update the values of 1 and 2. So 1 will become the whatever value of 2 we have, and 2 will actually be the total value. And at the end of the loop, we can simply return the value of 2. And this should define the total number of distinct paths we can take. Let's try to run the code. Looks like our solution is working. Let's try to submit the code. Yeah, our solution is actually 100% faster than all the other Java submissions, which is pretty good to have. And I hope you like the video. Let me know what kind of videos you want me to do more, and I will be doing a bunch of other videos on dynamic programming, so it would become more evident, and we will be able to grasp the dynamic programming concept together. Today we are going to work upon a very important dynamic programming problem, coin change, and which in my opinion everyone should do it at least 2, 3, 4 times until you get a real grasp of the concept on how to solve it. And let's understand the problem statement. We are given an integer array of coins representing coins of different denominations, and we are also given an integer amount that represents the total amount of money that we want to generate. Now we need to return the fewest number of coins that we can use to make up to the amount that has been provided over here. And if the amount of money cannot be reproduced, we need to return -1. Let's try to understand this by an example. So in the given example, the number of coins we are given is 1, 2, and 5, and the amount we are given is 11. So based on the example, we can clearly see that the most optimal way we can create this 11 is by using 5 plus 5 plus 1. So in general, this sums up to 11, and if we see the number of coins, we are actually using 3 number of coins to generate this value. If we look at the second example, basically we are only given 1 coin, the value number 2, and the amount we are given is actually 3. So no matter how many times we use the number of coins 2, we cannot generate this amount 3. So in that case we need to return -1, while in this case we would be returning 3 because we are using these 3 coins. So once we have this clear, now let's try to understand that what could be the different approaches we can take to solve this problem. The first approach that comes to our mind is actually to use a greedy approach, where whenever we are given the number of coins, so let's take one of our own custom examples, and we also need to keep in mind that whenever you are solving or giving any FAANG interviews, make sure to have your own custom inputs, because FAANG companies really like this kind of stuff, and that shows that you are able to think outside of the box, and you can also create test cases on your own. So suppose we are given an input like this, and the amount we need to create is actually 8. So in our greedy approach, basically we at any given moment for the given amount, we will take the biggest coin that is smaller than this amount and keep repeating till we reach this amount. Now let me show you that why this approach won't work. Because if we see here, the amount we have is 8, and the biggest denomination of coin we can create that is lesser than 8 is 6. So if we take this, so let's create our answer where we keep track of how many coins we are using. So we use 6 over here. We take 8 to 6. So we subtract 6 minus 8. We get the remaining value is 2. So since the remaining value is 2, we cannot use these 3 coins anymore because they all are greater than 2, and if we were to subtract this coin from 2, our result would actually become negative. So we cannot use that, but we can still use value number 1. So if we do that, and if we use the coin number 1, because this is a greedy approach, so we will add the coin number 1 to our answer as well, and so now the remaining value will be 1. So again we cannot use these 3 values, but we can still use 1. So we will use 1. The remaining amount is 0, which means that we have reached our total amount of 8, and we would add the value number 1 over here. Once we do that, essentially if we calculate in the answer, we are using 3 separate coins to reach the amount 8. So our answer would be 3 in this case, and we would return 3. But notice that this answer is actually not the lowest number of coins we can use. Actually, if we just use the coins 3 and 5, we can simply create this value 8, and our result in this case should actually be 2, not 3. So greedy approach doesn't work at all. Now let's see what could be the next approach we can take over here. We are given an input like this, and we need to reach out to a particular amount 8. So at any given point, if we basically start calculating from 0, and we will keep on making choices based on the number of coins we have until we either reach to this value 8, or our choices actually becomes greater than 8. Until these two things happen, we can keep on making choices given our coin denominations, and based on that we can actually create our own decision tree. And in the decision tree, whenever we reach at value number 8, we will keep track of the value, keep track of the path, and based on that path we can calculate that what are the minimum number of iterations we have to make. So initially we are at 0th position. So from 0th position we have 4 options that we can take. So let's make these 4 decisions: 1, 3, 5 and 6. Now at every single decision we still have 4 more decisions that we can take to reach out to this value 8. So again at value number 1 we still have 4 more decisions we can make. So let's do that. And again at every single iteration we still have 4 more decisions, and with every decisions we come closer to this value number 8. So initially over here complete 8 were remaining. Over here we are only dealt with creating the value 7, because we already used 1 coin. The remaining value would be 7. So over here the remaining value would be 1. Over here the remaining value would be 2. Over here the remaining value would be 4, and over here the remaining value would be 6. And suppose we continue on this path again, we would still have 4 choices. And notice that the remaining value we wanted to create was 6, which we are able to achieve over here. So the sum for this particular path, 1, again 1, and then again 6, is actually 8, which means that we have found a potential route. And if we see the number of coins we had to use 1, 2 and 3 coins. So current answer we need to return is actually 3. And since we have found this route, all the other routes, if you see, the values would not reach to 8, and we can cancel out these values. And basically because if we keep going on, we will still have to make more decisions, and the number of route will definitely be greater than 3. So we can start eliminating these routes, and we have one potential route over here. Again, if we keep on going down this path of 3 and keep making more decisions, we would end up with an result that would be greater than 3, or we would not reach 8 at all. So we can ignore this. Again, we can ignore this from 5, and at 6 we would still find a root something like this, where, because notice, even at 6 we still have 4 decisions we can make. So we can we can choose either 1, 3, 5 or 6, and notice that only one is remaining over here, and we can select this one. So we would have another potential route starting from 1 going to 6 and then again going to 1, that sums up to 8. But again, for this route as well, we need to use 3 coins, so our answer will still remain 3 and it won't be changed. But this is where we find another answer, and now we have exhausted all the possibilities from value number 1, so we can just ignore all of this. Let's get rid of it, so we have something that is more clear and not so much congested. Now let's try to see that what could be the possibilities from this value number 3. So even at value number 3, the remaining amount we have would be 5, and at value number 3 we still have 4 more possibilities that we can choose from: 1, 3, 5 and 6. And notice that in all of these these 3 possibilities, we would not reach 8. So we would not reach, basically the remaining value would not be 0, which means, but if we get down over here 5, over here only 5 is remaining, and we directly have a coin 5 present at the decision tree 3. And if we calculate the route would look like 1 and then 2. So basically we are only using one coin over here and we are using second coin over here, so we are only using 2 coins to reach to this value 8. So we can simply update our answer, that we have found a new minimum value that can come up as our answer, and we can set the value as 2. Now we can continue to search and keep on making more decision trees, and even for those nodes we will continue to making further down decisions to see if we can find a better answer, but we won't be able to find a better answer than 2, and eventually we would have to return this value. So this solution, in a way, it works, and it works as expected. At least we are getting the answer. But the issue with this approach is that time complexity is actually so bad. It's not even in polynomial time, it's simply in exponential time. And the time complexity, suppose the amount we are given, if we consider it as m, essentially until we reach this amount m, we are at every time keep on making multiple decisions based on the number of coins that are given. So we can compute the time complexity as big O of m to the power of n, where m is the given amount and n are the number of coins that are present at any given moment. This is such a bad time complexity that we, even if we ask NASA to run this command, they won't be able to do it more than up to a certain values, and we need to find a better approach. And in the optimal solution, we are simply going to use just 2 golden words: dynamic programming. And let me show you how we can solve this via dynamic programming programmatically. And we are just like a rational person. We are just going to think it in terms of intuitively, that if we are given this problem just to solve on a pen and paper, how we are going to do it. And one approach is that we can basically start from the value number 0. We can keep on reaching towards the amount we want to reach out to, and for every single element that we have found, we will find that for 1, 2, 3, 4, how many number of coins it took us to generate that particular amount. And once we are sure with this value, whatever value we have generated, the amount for 1 or amount for 2, we would be able to use this later down the road. And let's take an example. Let's continue with our example and see how can we achieve that. So we are given the example 1, 3, 5 and 6, and the amount we want to generate is 8. So initially we would create an array of amount from 0 all the way up to amount of 8, and we will initialize all the values by any value that is higher than 8. So let's say 8 plus 1, and now we will start with our solution. So far all the values are actually 8 plus 1 in this amount array, and this represents that these are the number of coins that are needed in order for us to generate any particular value. Now if we just want to generate 0 coins, how many number of coins do we need? Well, answer is pretty trivial actually. We simply need 0 coins, and this becomes our base case. So now let's say for the second value, amount of 1, that if we want to generate value number 1, how many distinct coins we need. So whatever value is, we will check first of all in our coins for all the values that are given in the coin, to see if we can directly use, if the given coin is lesser than the value we are trying to achieve, can we use that coin. So since the value is 1, we can clearly see over here that this 1, if we just use one coin, we would be able to generate this value 1. So the answer in this scenario becomes pretty simple, that if we just use one coin, we would be able to generate this value. And notice that for value number 1, we cannot use any of these 3 coins because they are all greater than our value 1. So there is no point in using them. Now let's repeat the process for amount 2. So for amount 2, if we want to generate the value 2, how many minimum number of coins we need? So first of all, let's check with the first value. Okay, so coin is actually less than 2, so we can use this coin. We will use this coin. So if we use that coin, basically we have already used one coin so far, and since we use coin number 1 and we want to achieve value 2, we can say that now the value we are trying to generate is actually 2 minus 1. So again, value number 1. Now we want to generate value number 1, and if we can do either two things. Either we can go back to all these coins, again we try to generate that value, or notice this beautiful thing over here, that we have already calculated that if we want to generate amount 1, how many coins we are going to need. So why are we being so picky, and why are we doing all this extra work, and why are we making our lives miserable, our CPU's life miserable by doing all these additional calculations? Why can't we just store this somewhere, and if we have stored it, we can simply use it over here. So in this case, we can say that we have already used one coin in order for us to generate this one, and now once we have generated this one, we know that the number of coins that are needed to create value 1 is already computed. So we will do 1 plus amount to generate one coin, and this would be the answer if we want to generate the value 2 from the given coins, and this would become 1 plus 1, so 2, and this would be our direct answer, and these are the minimum number of coins that we can use to generate value number 2. The reason I'm emphasizing so much on this is because this exactly is the core concept of dynamic programming, and we have just hit a very big hammer to its head. Basically, we have said that, hey, I'm going to take this dynamic programming all the way, I'm gonna chew it, swallow it up, so it becomes a second nature to me. And now let's continue with our example. This is going to be a really long video, and I recommend that if you just understood at any point, I would just suggest you to go ahead and start skipping over. So now the value for amount 2 is actually 2. Now let's calculate for amount 3. If we look at for amount 3, we have two options. Either first of all we can start with this value 1. We'll take value 1, then again the remaining value would be 2, and we have already calculated that what is the amount that is remaining for value number 2 over here. So if we, let's take that approach just for the sake of understanding. So first of all, we use coin number one. So we use coin number one, and plus the amount that is remaining is actually 3 minus 2. So we still have amount 2 that needs to be computed in order for us to achieve this value 3. So we can say that for this one, the way we can do it is one coin that we already used plus whatever the amount 2 that we need to use. And notice amount 2 has already been computed over here. So we can say that 1 plus 2 equals to 3. So if we choose one of these coins and we try to achieve the value number 3, initially we would be able to find our answer by using minimum of 3 tokens. Now again we notice that now since we have computed this coin, we notice that 3 value number 3 is actually less than or equal to this given coin 3, and we can use it to our advantage. So now we know that we want to achieve value number 3 over here. If we just use this one coin, we would be able to achieve this amount number 3, and current minimum amount that we have calculated that is that we need minimum 3 coins in order for us to achieve value number 3. So why are we using 3 coins? Because our aim is to use the minimum number of values. So we can simply just say that if we just use one single coin that is of denomination 3, we would be able to calculate the result as 3 for this amount 3, and we won't be able to do anything with these two because they are already greater than 3, so we can't make 3 with those denominations. Now let's move forward with our with the next value, amount of 4. And if we generate the amount 4, how many number of coins we need? So basically if we just take this first coin, we know that we have already used one coin, and plus we have the value remaining as amount 3. Amount 3 is already computed. We are using the best knowledge of computer processing we can, and based on that we can simply determine that, oh, and by the way, this would be 1 not 3, my mistake. So we can just simply say that if we want to generate amount 4, we can do 1 plus amount 3 is already 1, so we can use 2, and this would be the minimum solution, that even if we use the first coin as 3, we would use second coin as 1, and still we will get the same answer. So I'm not going to do whole computation, but you get the idea. So for amount 4, we can say that 2 are the minimum number of coins we need in order for us to generate amount 4. If we want to do amount 5, how many coins we need? And the answer is pretty simple. We already have this 5 present over here, so we can just simply write 1, and notice that we are going to check all the coins, and when we get to 5, we will be able to say that this is the minimum number of coins we can use. Next is amount of 6. If you want to generate amount of 6, again the answer is 1, because we are already given a 6 over here, and we are going to check through all the coins that are less in the value of whatever the amount that we are trying to calculate. Now let's calculate for amount of 7. If we are calculating for amount of 7, and if we check for the first coin is actually 0. So basically we can just simply say that the first coin is actually 1. So basically we can just simply say that we have already calculated the one coin, plus now we need to calculate the amount 6, because 7 minus 1 is equal to 6, and we already have the result for amount 6. So we can just simply write that we need at least 2 coins in order for us to generate the value number 7. And now let's try to calculate our output that we have already given that we need to calculate the 8. So if we want to calculate amount 8, and based on this table, it becomes pretty simple initially. So first of all, we will calculate this with value 1. So basically we would be doing the calculation something like one coin that we have already used plus amount of 7, and we know that amount of 7 from our previous computation is actually value number 2. So we will do 1 plus 2 equals to 3 for this amount 8 that we are trying to calculate. But can we do something better? And remember that we are going to check all the coins. So because we are going to check all the coins, when we get to coin number 3, our solution would be that we have used one coin, and that is the coin value is 3. And because we have used 3, now we need to generate the amount 8 minus 3 equals to 5. So we can say that we used one coin to generate the value 3, and now we need to generate value 5 in order for us to achieve this amount equals to 8. So if we do 1 plus amount of 5, what is the answer? And the amount of 5 is already calculated over here as 1. So we'll just simply use that value, and we'll do 1 plus 1 equals to 2. And we will carry on with our computation with this value 5. Again, we will find the answer 2 because we'll do 5 plus 3. And when we get to value number 6, we will again find the answer to generate the amount 8 as 3, because we'll do like 6 plus amount of 2. So the minimum number of coins that we can find in order for us to generate value number 8 is actually 2, and we can simply return this value 2. Now notice that we also have to take care of the scenario where we cannot create the amount based on the given coins. And if we cannot create the amount at the end of our computation, the value for amount would amount of any given, let's say 8, that we cannot compute in this case, would actually be the value 8 plus 1, so equals to 9. Because notice that at the beginning of our array, this is how we initialize the values to. And if after all the computation we found that the value of amount is actually the original by default value that we set, which is amount plus 1, if that is the case, we know that we are not able to generate this value, and we are not able to make any impact with our solution because the coins cannot generate this value. We will simply return -1, and this solution would work perfectly fine. This is a really beautiful solution, and if you go through with this approach in your interview, you are gonna just be very impressive candidate, and all the FAANG companies would want to hire you. So let's calculate the time and space complexity. So time complexity for this one would be actually big O of n times m. Now why n times n? Because we are running the loop to calculate the value n, and n is actually the value of this amount of whatever is given. So we are going through a loop n times, and m are the number of coins. Because notice that over here for every single element we will have to go through all the coins in order to generate the value. So the time complexity would be big O of n times m, and the space complexity would be big O of n, because we are creating an additional data structure array to store all these values, and the values we are storing up to is actually the amount, whatever amount we are given. So we can say that the space complexity would be big O of n. Okay, so let's create an array amount, and its size would be amount plus 1. We fill out all the values inside the amount as amount plus 1. This would help us determine that whether if we cannot create the value, we need to return -1 or not. And now we will set up the initial value for amount of 0 would be 0. Now let's create our loop. So we will start with I equals to 1, because we have already calculated the value for amount 0, and while I is less than or equal to amount. Now notice that for every single value of I, we need to calculate for all the values of coins. So we will have another loop that would iterate over coins. And first of all, we will check that if our present I is actually greater than or equal to whatever value of coin that we are comparing it with. So if this is true, then only we will check that whether what is the amount for any given j, any given I. So we'll do a minimum value of either the value itself, so whatever value we already have, or we will take one coin of any j and we'll do an amount of I minus j. And yep, this is the main logic, because in this logic we are calculating all the amounts and we are using it further down the road as well. So after this iteration we just need to check that if for any given amount, so amount of amount, if that is less than the value amount plus 1, which means that we have been able to generate this amount. So in that case we would return whatever the value we found, else we can simply return -1. Let's try to run this code. We made a silly mistake. Again. Oh, we need to check with coins of j. Yeah, looks like our code works. Let's try to submit this. And yeah, our submission is actually pretty efficient compared to others who have submitted. Today we are going to do a very important LeetCode medium problem, longest increasing subsequence, and I have decided to break this video in two parts. In the first part I'm going to discuss the brute force solution and an accepted solution for this problem, and in the second part I'm going to show the optimal solution. But the thing is, the optimal solution is really difficult to achieve and it's a little bit tricky to come up with. So let's understand the problem statement. Basically we are given an array of numbers and we need to find the length of longest strictly increasing subsequence. So subsequence means that suppose we are given an input like this, 1 2 4 5. So we can say that the value 2 and 5 is actually a subsequence of this given initial problem. Let's try to understand that what is the input given. So we are given over here an 18, and this example, and if we take these numbers 2 3 7 and 101, this would be our longest increasing subsequence. So if we get rid of this value 5, this would be the longest subsequence we can make, where all the values are in increasing order and the length of all the values would be 4, which is what we need to return as a part of this output. So once we know the problem statement, let's see that what could be the brute force approach. So in the brute force approach, we are simply going to take every single subsequence that we can possibly make, keep a parameter that tracks the length of any subsequence, and eventually at the end we should be able to find a subsequence with the maximum length. So let's take a small example and see that what are the possible subsequences we can make. So suppose our given input is 5, 3 and 8. I'm only taking 3 elements because I need to show that why this approach is bad and what are the possible subsequences we can make out of this. So let's start making all the possible subsequences. The possible subsequence would be 5, 5, 3, 5, 8, 3, 3, 8, 8 and 5, 3, 8. These are the possible subsequences we can make out of only these given 3 problems. And if we check the length of each of them, and if we find out the property that which one is a strictly increasing order, we found that this is the strictly increasing order and the maximum length we can achieve is 2. So this solution works, it works fine. The problem is that notice that we are only given 3 elements over here, and based on this 3 elements we were able to make almost 7 subsequences. Mathematically it's actually 2 to the power of 3 minus 1, and for any single given n, this is the number of subsequences we can make. So suppose we are given n values in the given input, the number of subsequences we would be able to make would be 2 to the power of n minus 1. So if we calculate the time complexity, we can just say that the time complexity is actually big O of 2 to the power of n, which is extremely horrendous time complexity, and this is exponential. So even with enough numbers, even NASA won't be able to solve this one. So let's move on to the next approach. Now we want to find the better approach, and we know that the way to do is to use dynamic programming. But the thing is, how can we identify that we need to find the solution using dynamic programming? Also, what dynamic programming solution are we going to use? So I'll be discussing both the things in next portion. And first of all, let's take an example. We'll try to see how we are going to solve it. Then I'll show you how we can determine that we are using the dynamic programming, and after that we would be implying the result, and I would be showing you the coding example. So suppose our given input is, suppose this is the input given, and we need to find the longest increasing substring. So just by looking at the given example, we can determine that the longest increasing substring actually exists between 7, 8, 16 and 27. And now let's see that how can we come up with this solution. How do we determine that this is dynamic programming? Suppose we are just given an example like this. We are just given one value, that let's say the value is 7. If we are only given 7, what is the longest increasing substring we can make? Well, the answer is quite simple. We can simply make just one substring of length 1. So this actually becomes our base case, that if we are only given one value, we are guaranteed to have at least one substring that would be the longest increasing substring that we can make. So now let's see that how can we use this logic. Say that for all the given elements, basically there exists one substring at least that is the longest increasing substring. Let's just mark all the values as 1. We know that if we are only given the value 10, the longest increasing substring we can make would only be 1. But when it comes to the second value, now we have something to compare to. Suppose the 7 value, if this was greater than 10 and we only had 2 values, we can say that at the second position, the longest increasing substring that we would be able to make would actually be whatever we have made so far plus 1. So we would have been made 2, but over here that's not the case, and over here the value 7 is actually less than whatever we are given the value before that, which means that the longest substring we have at the value 7 would also be 1. So this would be true in this case. But now when we come to 8, we have two possibilities. What are the total substrings we can make up until this point, up until 8? Okay, so for this value 8, what is the one thing that we can determine? We can basically determine that there are 3 possibilities of the substrings we can have and we can compute. One possibility is we could have a substring like 10 and 8. Second one is we could have substring 7 and 8, and third one is we could have a substring 8 by itself in case if all the values before 8 are actually greater than 8. So in this scenario, from 10 to 8, we know that 10 is already greater than 8, so we cannot create a substring over here. So let's ignore this scenario. For the second scenario, 7 to 8, actually this is a valid increasing substring because 7 is less than 8 and it comes after it. So what we can determine is that the longest increasing substring we can make at value number 8 would be whatever the longest increasing substring we have made up until this point. So whatever the longest increasing substring we have made for the value number 7 plus 1, because 8 is coming after 7 and 8 is just one step after it. So we can say that longest increasing substring at value number 8 would actually be whatever we have found up until longest for the longest increasing substring of 7 plus 1. And this is how we can determine that this should be solved as a dynamic programming problem, because in dynamic programming, basically whatever calculations we make in the past, we keep track of them in some way, either through an array or storing them in variable somehow, and based on those results we actually use it in upcoming future calculations, so that we don't have to calculate everything from the scratch. So this is one way we can determine that this problem should be solved using dynamic programming, because if we just look at the problem, we understand that we need to find the longest increasing substring, which means that we need to keep track of whatever we have calculated so far in the past, and using those results we would make decisions that whether we want to keep this current value or we want to ignore this current value. So this is a very important thing to keep in mind, and this is basically the core concept of finding the pattern whenever you are given that whether the problem is dynamic problem or dynamic programming problem or not. Because in the interview, the interviewer is not going to tell you that hey, this is a dynamic programming problem and just go and solve in that manner. So now let's again continue with our example. So we can determine that currently the value at 8, the longest increasing substring we could make at value number 8 is 1, but we just found that from 7 to 8 we can actually make a substring as well. So this bit would become actually 2, and we can say that up until the point of 8 the longest increasing substring we can make is actually 2 and not 1. Now let's move forward. Now let's consider for value number 5. At value number 5, let's again compare from 10 to 5. We cannot do anything because 10 is already greater than 5, so there is no point of doing this conversation. Let's compare 7 to 5. From 7 to 5 we cannot do anything because 7 is greater than 5 and also 8 is greater than 5. So at value number 5 there are no values that are less than 5. So at value number 5 the longest increasing substring we can make is actually size 1, because there does not exist a smaller number before 5 in our given input. So we'll keep this 1 as it is because we have already made all the calculations. Now let's calculate for this value number 16. And actually for value number 16, if you notice that all the values are smaller, so this would be a very good point for us to understand that how everything works. So from 10 to 16 we notice that 10 is smaller than 16, so there is a possibility. And basically we can say that whatever the longest increasing substring we have found at 10, if we do it plus 1, that would become 16. So the longest increasing substring for 10 we have found is actually 1. So 1 plus 1 equals to 2. So let's just update the value 2 over here, and now let's move on with our calculation. So we are done with this 10. Let's calculate with 7. So if we do 7 to 16, actually again we will do 1 plus 1 because LIS of 7. So 1 plus 1 is again 2. We already have 2, so there is no point in updating the value. Let's ignore this. Let's do again with the value 8. So from 8 to 16 we know that the value of 8 is actually 2. So over here at value number 16 we can say that increasing substring at value number 8 plus 1, so it becomes 2 plus 1, and 2 plus 1, okay, I made a mistake. I think this is 1 that represents 5, and the value for 16 is actually over here, so I'll just write it down. So LIS of 8 plus 1 is actually 2 plus 1, which is 3, which is greater than whatever the longest increasing substring we have so far. So which means we can update this value. So over here the longest we have found so far is actually 3. And now we can also create one more substring from 5 to 16. If we calculate from 5 to 16, we found that the value is actually 1 plus 1 would be 2, which is not greater than whatever we have at 16. So we can say that up until this point 16, the longest substring out of all of these values we can make is actually 3 for the values up until the point of 16. And let's move forward with our calculation. So again, the next value is 27. 27 is greater than all the other values. So if we do 10 plus 20, 10 to 27, we would find the value as 2. We'll do 7 to 27, we will find the value as 1 plus 1, again 2. We will do 8 to 27, we would find the value 2 plus 1 as 3. Again we will do 5 to 27, the value we would find would be 2. And at the end we would do 16 to 27, and we know that the value at 16 is 3. So we would be able to find the value as 3 plus 1. And because we have calculated all these results, we don't have to do calculations all the way from beginning, and we are just able to use the results we have stored so far. So we know that the maximum value we can find is 3 plus 1. So we would update the value at longest increasing substring at value number 27 to 4. And then we come to our last value, 9. So, and again we will do the whole thing for 9. So 10 is greater than 9, so we cannot do anything. 7 is less than 9, so we can for this one we can have the value as 2. 8 is also less than 9, so from 8 to 9 value we can have would be 3. 5 is also less than 9, so from 5 to 9 the value we would have would be 1 plus 2, 2. From 16 to 9 we cannot do anything because 16 is greater than 9, and from 27 to 9 we cannot do anything because 27 is definitely greater than 9, which means that the maximum value we could have find so far over here for 9 is actually 3, and that comes from the 8 plus 1. So we will update the value over here as 3. And now we just need to find that what is the maximum value we have found in this array that we have created based on the calculation. So basically clearly we can see that this value 4 is the maximum value we have found, and that would be our answer. That is what we would be returning as longest increasing substring. The thing is, we actually don't need to iterate over the entire array again. We could have actually done this when we are calculating or when we are making this array. We could have just keep track of one parameter called max, and we would compare it with whatever the value we calculate at each location. So whenever we find a new maximum value, we'll just store it in this value, and at the end of our loop, in this max parameter should have our final solution, and we can definitely return this, and this solution would work perfectly fine. Now let's calculate the time complexity. So basically the time complexity for this one would be big O of n square, and it's pretty simple to understand that because for every single element we are basically taking all the elements before that and comparing it with whatever the element we have. We did the same for every single element. So for n element n, we might have to compare it with n minus 1 values, so the time complexity becomes big O of n square. And if we calculate the space complexity is also big O of n, because we need to create this additional array to store all the values. And this is a good time complexity and good space complexity compared to our brute force approach. Remember our brute force approach, the value we had was actually 2 to the power of n, which was way higher. This was almost exponential time complexity, and we have done significant improvements from this one, and we have actually moved to n square. So this solution would work perfectly fine in any interview. And I'll move on to coding, but the thing is I would be making another video to explain that how can we solve the same problem using n log n complexity. And this is actually pretty ideal, and if you can achieve this in any interview, if you can come up with this time complexity right then and there in the interview, you can be guaranteed that you would be placed in any company you want. So let's move on to coding now. So first of all, we will create a new array called lis, and we would create the array of size, whatever the size we are given for the input nums. And we will initialize the array with value 1. We will also create a parameter called max that will keep track of the maximum longest increasing subsequence inside the loop, and we will initialize the value as 1. So now let's create our two loops. So first of all, we will create a loop that is starting at position number 1, not 0, because we need something to compare to, otherwise all the values would be just 1 before that. And we will run it till the length of the given array. Well, now this would be our inner loop, and we would start it from position 0, and we will run it all the way up to the position I. Now inside the loop, first we need to determine that whether our current I that is on the right side of the array is actually is actually greater value than whatever our j is. If that is the case, then only we would move forward with the calculation. So if I is greater than j, now we will do our calculation for the dynamic programming. So the value of I would actually be the maximum value we can achieve for whatever lis of I we already have, or 1 plus whatever lis of j we have achieved. And this would be our recurrence relation. I guess that is what it is called in dynamic programming. So this is just to keep in mind that yeah, if you mention that this is the recurrence relation, it sounds really good impression. It sounds cool as well. And also we check that whether the current lis value is our max or not. So we'll just check the existing max value with the new lis that we just created. And yeah, I think that's pretty much it. After this loop runs, we can simply return whatever we have found for the value max, and this should be our answer. Let's try to run the code. I think we made some silly mistake. Yeah, looks like our code is working. Let's try to submit it. And our submission works, but if you notice that our submission is not actually the best submission, it's only faster than 55.54% of the online submissions, and that is because our this solution is actually work in big O of n square times. Today we are going to do a very interesting lead code problem, longest common subsequence. And unlike many other interview questions, this actually is a very good problem to solve because it does have real life use cases which almost all computer engineers use on a daily basis. Basically, GitHub is one of the prime example that uses the solution of longest common subsequence in its functionality. This is going to be a really long video because I want to make sure that I be as thorough with my thought process as I can, and that is why I have decided to break this video in different chunks. So if you are comfortable, feel free to directly jump to that portion, and this is the approach we are going to take. We'll understand the lead code problem. We are going to come up with a primitive solution using recursion. Then we will see that how can we use memorization to improvise on the recursive part, and then we are going to see that how can we use dynamic programming to get the optimal solution. And basically, once we have the optimal solution, we are going to write the Java code for it. So let's understand the problem. In order to understand the problem, first we have to understand a very key factor, that what is a subsequence. Basically, if any value is given, suppose we are given a string a is equal to x, y, and z. A subsequence is any elements that are present in this given sequence, though they might be out of order. So x, z is a subsequence, y, z is a subsequence, y by itself is a subsequence. But if we consider like yx, this is not a subsequence, because if you see the order in which they are represented over here is not the order in which they are represented over here. So just keep in mind. And now once we have it clear that what a subsequence is, let's understand the problem statement. So we are given two strings, text1 and text2, and we need to return the length of their longest common subsequence. And if there is no longest common subsequence, we just return 0. So let's take it by an example that is given over here. So if our A is A, B, C, D, and E, and B is A, C, and E. So now we need to find the longest common subsequence. It's pretty simple, that if we just draw the lines, we can determine that A is present in both the cases. C is also present and E is also present. And notice that there exists this B and D, but if we remove this B and D, basically A, C, and E will remain same in for both the strings. So we can say that A, C, and E are a subsequence that is present in both the places, and we want to return their length. So in this case, the length would be 3. See that what should be the most primitive approach to solve this problem. Once we understand that, we are going to make improvements to it, and based on the improvements, we are going to come up with the optimal solution. So basically, most simple thing that you are going to do is compare every single element with every single other element. Keep on doing it, and whenever you find a match, do something else. So let's see that what should be the approach. We will start by checking all the elements from first element to this element in the B. We don't find any match. Okay, we move on to the next one. Okay, now again we do the same thing. Over here we find a match. The moment we find a match, now we need to find the longest common subsequence. The way we are going to find longest common subsequence is only by eliminating whatever we have calculated so far. So the thing is, now the area of calculation that we are going to achieve is actually limited to up until this point and up until these points on the B side. And the reason we are going to do the reason we have to do is because if we don't do it, if we just move on to the next element, basically we are going to lose that connection that we have made at this point A, and we need to find the longest common subsequence. So after this my long speech, let's see that what should be the way forward. Now we again start comparing with C, but now we are only going to compare with these three values. So C to I, no match; C to X, again no match; C to B, again no match. So we don't find any value over here. Again we repeat the same process for this K. So again there is no match. But now when we come to this I, yes, we find a match. And when we find a match, we repeat the same process. So the process is that now the area of a search that we have to perform on the first string, and on the second string we only have these two elements that we need to consider. So let's do the same thing. Compare E with X, nothing, and E with B, nothing. So we have found something. The thing is, we cannot stop right here, because there could be a potential better substring that was not caught over here, but it might very well be hiding somewhere later in the picture. So what we do so far, we store the value whatever we have calculated over here, and the substring we have calculated so far is of length 2. The values are A and I. And now once we have this value, we will again repeat the same process that we were doing. Now we will again check with this C with all the other values of this B substring. So we find a match over here at C, which means again the area of interest reduces. Now we only need to check for these three values, and we only need to check for these values on the lower substring. And when we do that, let's repeat the same process. And so far we have found one common element. so we can put 1 as common element. And now we jump to the next elements. When we jump to the next element, this k, okay, again we found a match, so we do 1 plus 1. Our area of interest again shrinks down. Now it shrinks down to only these 4 elements on the bottom string and only these 2 elements on the top string. Again we repeat the same process. We check with I, we don't find anything. We check with I, yes, we find something. Once we have found over here, so we do addition over here again, and now our area of interest again shrinks down to only this element and only these 2 elements. Again we do the check, and yeah, we don't find anything. So far the longest substring we have found is actually 3. We compare 2 to the 3. Okay, 3 is greater, so we are keeping 3 so far. But the thing is, we are not done yet. We are not out of the woods yet. We'll have to check for all the other remaining values as well. So what would be the remaining values? So far we have checked until this J, A and C. Now we again repeat the same process from this K. Okay, K to K, there is a match. Again we will find K to I, there is a match. The longest common substring we have made so far is only 2, but 3 we already have a better substring, so let's keep it on the side. Now we have calculated the values for K. Now again let's repeat the same process. Again with I, we compare all the values. Okay, we find the substring over here from this value I. Again this is only 1 and we don't find any other values, so we are done. Now we are at the last element E, and again we check with all the values of B and we don't find any substring, so we are done over here basically. And this is the most primitive approach. Now let's try to see that based on this we have found 3 conditions so far, and using these 3 conditions, the most common algorithm we can write is a recursive one. I mean, you can write an iterative algorithm as well, but recursive is just less code, and I have already written that for you. So let's go over the algorithm. We have 3 conditions. First condition is at any point if we reach the null value, we can't return anything, so we return 0 basically. This is our terminating case, and eventually we will reach to this position. Now notice that we start at position 0 on first and second substring A and B. Now second case is that we find out a match, that the value of whatever I and J is for B is actually same. If there is a match, we do this process. So whatever the way we calculated these values, so we simply do 1 plus whatever the remaining amount or whatever the remaining area is left on the substring, and that is what we are doing. So we do an addition of 1 and we again repeat the same process to finding the longest common substring. And now notice that we increased both the values of I and both the values of J. And if that is not the case, if we don't find a match, which is going to happen on most of the cases, if this happens, what we can do? Well, we can find the maximum value we can find amongst the remaining substrings. So what would be the remaining substring? Suppose the value is, this one is A of I and this one is B of J. We are at these 2 positions, we don't find a match. What we are going to do? We are simply going to check from the next value onwards whether there exists a potential match. If it does not exist, we again jump to the next value. Again we check for the same thing. If we want to write it in a different manner, we can do the same thing at B over here as well. So if we are at B of J, we don't find a match over here, what we can do? We can just simply go to the next value, keep on checking with A. If we find a match, good. If we don't find a match, repeat the process. So in either case, and whatever we found, we need to return the maximum value we have found, because we need to find the maximum longest common substring. So we do an A of I or A of, and B of J plus 1, or A of I plus 1 and B of J. Whatever is the maximum that we get, we just put it in our result. Now since we already know this, let's try to solve the recursive problem with one of our own custom example. I have taken a very small example and you'll know soon why I'm just taking a pretty small example. So let's start with A of 0 and B of 0. So A of 0 and B of 0, the values are J and R. There is no match, which means now we have 2 possibilities. Either we do A of 0 and B of 1, or we do A of 1 and B of 0. So let's expand on this left subtree for now, and then we will do the remaining portion. So again, now over here again we have so what are the values? So it's J and O. So J and O, there is no match. So again we have two possibilities. We can either do A of 0 and B of 2, or we can do A of 1 and B of 1. So A of 0 and B of 2, again we found the value J and N, there is no match. So we move on. If we move on, again we do A of 0 and B of 3, but notice that B of 3 is actually a null value over here. So since there is a null value, we cannot return anything over here, so this becomes 0. We return 0. Now we still have, do we still have possibility? Yes, we have possibility over here as well, that we have the possibility to calculate A of 1 and B of 2. But now let's again elaborate on this portion. So this A of 1 and B of 1 is value O. Okay, so O is a potential match. So yeah, that's good. Both values are same, which means that we can do 1 plus over here. So now we have done 1 plus, and now we need to do the whatever the longest common subsequence we found for A of 2 and B of 2. So A of 2, the value is H, B of 2, the value is N. There is no match. So because there is no match, again we move forward. So we have two options over here. We can either do A of 2 and B of 3, or we can do A of 3 and B of 2. So A of 2 and B of 3, we already know that B of 3 is null value, so we can return this as 0. So we haven't found anything on this side, and we cannot move forward. Over here, A of 3 and B of 2. So A of 3, the value is N, and B of 2, the value is also N. So over here we find a match, so the value is N. Bingo, which means that we can do 1 plus over here. So the maximum of these two is actually 0. So there is nothing else to calculate. But the thing is, we already calculated a match over here. So there is 1 plus 0, which means the value for this A of 3, B of 2 is actually 1. Now because this value is 1, we again do a comparison between these two values. So 0 and 1, 1 is obviously greater, which means that the result for this A of 2, B of 2 would be 1. Now over here the value is 1, and this we already had a match, which means we need to do 1 plus whatever value we have found of A of 2 and B of 2. So the value of A of 2 and B of 2 we have found as 1. So we will, over here the value of A of 1 and B of 1 would be 1 plus 1 equals to 2. Over here we have found the value as 0, and over here the values we need to compare to with is 2. So obviously 2 is greater, so we are going to store the result of A of 0, B of 1 as 2. And now we'll need to calculate the right side of the subtree. When we calculate the right side of the subtree, we are actually calculating the values A of 1 and B of 0. Now A of 1 and B of 0 is actually, again we have two possibilities. We can either do A of 1, B of 1, or we can do A of 2 and B of 0. Now notice that this A of 1, B of 1, does this seem familiar? Yes, it does, because we have already calculated its results right across, right very next to it. Let me clean this up a bit. So we have already calculated this result, but the thing is, we are still going, and will eventually keep on going, and then we will try to find the solution, and eventually we will be finding the solution as 2, because there is the longest common subsequence we have over here is of value 2. But the thing is, what are the issues with the recursive approach? Well, the issue is pretty common. The time complexity is actually 2 to the power of n. And why it is 2 to the power of n? Because at every single location we have two options, whether we can choose it or whether we cannot choose it, whether we can choose it or we cannot choose it. And pretty soon, within just few elements we had over here, I couldn't even draw the entire subtree on this side. Why? Because the values were simply growing too big, and this is the problem with the current recursive approach. But the thing is, how can we tackle this current recursive approach? Well, the reason is just right. The answer is just staring at us, and it is right over here, that because we are doing a lot of repetitive work, and somehow if we somehow have a way to store whatever the results we calculate over here, And if we just put those results, apply the logic over here that okay, if the values are null, we return 0. If the values are same, we return whatever the value of 1 plus the I plus 1 and j plus 1. Or and if values are not matching at all, we simply check that what is the maximum amount we can reach to either comparing the next value on the a string or comparing the next value on the b string. And that is how we would be able to calculate the result. If we somehow store these values and use it in our approach, we would be able to compute this pretty faster and not in this exponential time. And the art of storing the values of the recursive function in some form to use it later down the way is actually called memorization. So if you want to put a definition, just like made up definition, you can create a definition like this, but it's actually really interesting to understand. And so let's see that what could be the approach. Okay, so now let's try to use memoization, and we are going to use the same example. Now between these two values there can be three possibilities that we can have between any given elements. The possibility is either the element is null. If any of the element is null, we simply return 0. So that's base case. Either both the values are same. So if the values are same, we simply need to do 1 plus least common element of whatever we have found. So a of I plus 1 and b of j plus 1. But what this and suppose if this is a of I and b of j, so what this a I plus 1 and j plus 1 represent? If we take it in a matrix, suppose this is the value we are considering, and we found that okay, there is a potential match over here between these 0 0 values. So 1 plus LCM of this would mean that whatever the value we have over here, because this would be 1, this would be 1, so whatever we have value we have in diagonal, if we do 1 plus that value, we would find the answer that lies at this position. So just keep this in mind, we are going to use it somewhere. And the second and the last option is that the values are different. If the values are different, we know that we need to find the maximum value for any I and j values that are different. We need to find the maximum value between I plus 1 and j, or j plus 1 and I. So amongst these two, and I and j are respected for a and b, so just keep in mind. So if we look at this, we can determine that basically, suppose for this particular element, we need to determine that what is the value for this one. And we realize that okay, the value over here is suppose x and y, so they are not matching. So we need to find the maximum value. So currently this position is 1 and this position is also 1. So what are the two possibilities we have? We could have a value at position 2 1. So position 2 1 would be the value over here. So whatever value we have over here, and second possibility we can have is position 1 2. So position 1 2 would be over here. So we need to find the maximum value amongst these two. We need to find the maximum values amongst these two in order to calculate that what should be the value for this value, this one would be. And now we have these three things, we can actually use it in our matrix. So let's start filling up the values over here. First we determine that the value and first we determine that okay, j and r for this position, the values are not matching up. If the values are not matching up, we need to see that what is the maximum value returned between these two values. The thing is, we don't know these two values yet, but keep in mind that this should be the approach. Now again over here, that the values values are not matching up. So for this position, we need to find the maximum value between these 2 points. Again over here, the values are not matching up, so we need to find the maximum values between this and this point. The thing is, we have a null value over here, so this will always be 0. So whatever value we have stored over here, we can just impart that value over here, and that's pretty understandable. Again, if we look over here, this position, again the values of O and R are not matching. If they are not matching, we again repeat the same process. Now over here, actually we have a match. Actually this O and O matches. So if we have a match, we choose a different approach. We basically go on the right side, now go on the diagonal, and whatever value we find, we do an addition with whatever value we have on the diagonal of that. And again over here there is no match. So if there is no match, we need to find the maximum value between these two. Now we keep on repeating these things, and the only number we can calculate so far is actually this last one, the value of n, where, because okay, over here both the values are same, so for this position we can say that this would actually be 1 plus diagonal, and over here in the diagonal we have null value, so basically this would result up in 0. So we can say that so far over here the value of n would be 1. But the thing is, this is a really important property. Based on this we can do a lot of things. So let's try to do those things over here. So currently our n is 1, and so far what are the common values we have found? Basically the common values we have found is only over here. So over here I'll just mark it as something to indicate that this is the common value. All the other values, they are not matching up apart from this 9. So now for this value we can say that the result would be whatever we have over here and over here, but this is null, this is 0, so we can just impart this one. Again we can do the same thing, and again we can do the same thing. Now even for this particular position we need to find the maximum value between this point and this point, but the thing is over here the value is null, so nothing exists over here, and this value is 1. So again we can impart the same thing over here, and same happens for this position. So we have filled these values so far. Based on these values, okay, now over here the values are not matching up. If the values are not matching up, we do maximum of next element or bottom element. So both are 1, so we can again do 1. Now at this particular position, and again over here we need to do maximum of this and this, so again we do 1. But now for this particular position we still have a match between this O and O, which means we need to do a diagonal plus 1. So if we do diagonal plus 1, in the diagonal the value we have is 1. So if we do diagonal plus 1, we actually get the value as 2. So this becomes our 2. And now for this position we need to do a maximum of these two values, so that's obviously 2. Again for this position we need to do maximum of these two values, again the value is 2. And for this position we need to do maximum of these two values, so the answer is 2. Now at the end we can simply return whatever we found at 0th position, and this would provide us the maximum longest common substring we find. And we are able to calculate this because we actually stored some of the values in memorization. We went over the matrix again, we implied the logic we have defined over here, that if the value is null, return 0. If the values are same, do 1 plus diagonal. If the values are different, take the maximum value of either next element or bottom element. And that enables us to find the answer of this problem, and actually n to the n times m, and using that we can actually find the solution of this problem in big O of n times m complexity. Why we are able to use this big O of n times m? Because we need some time to create this array, this matrix, and once we have this 2D matrix filled up, we just need to iterate over it, and eventually we would find our answer. So very important property to understand, and very easily we can do this thing. The thing is, notice over here that we are still doing bunch of things, and we are doing a lot of repetitive work, because during the first iteration we don't even have any values to compare to. So now what can we do? So again, the beautiful words dynamic programming can be used over here, and dynamic programming can actually solve this problem. Now suppose in the dynamic programming we are again considering the same problems, and what should be the index value? It would be 0 1 2 3 and 0 1 2. The thing is, notice over here that we actually create a matrix with one value addition for both these two lengths. So let's see that what the values would be. So over here this would be John and this would be Ron. Now for this additional values 3 and 4, we can actually say that this value is basically null and this value is also null because the string ends at this position. So once the string ends, we can actually, and we know that if we encounter the null value at any moment, the value for that portion is actually becomes 0. So if this is 0, we can already pre-fill these values. So let's do that. So this would be all these values would be 0 and all these values would be 0. Now we have all these values as 0. We can start filling up our matrix, and using that we will be able to compute things pretty fast. So let's see that how can we start filling up our matrix. By the way, we can fill up our matrix in two ways. We can either start at the bottom position and go up and side, so eventually we will reach over here, or we can actually start at this position and eventually we will reach at the end. So it's up to us that what approach we want to consider. I'm just starting at the bottom and now we are here. That's a bad pun, but okay. So this particular position, we know that the value, there is a match. So if there is a match between n and n, we need to do 1 plus diagonal. Diagonal is 0, so we can fill up this value as 1. Now for this particular value, there is no match. We need to do whatever the maximum of diagonal, so the value becomes 1. Over here again we need to do maximum of diagonal, so the value becomes 1, again maximum. And on this particular row column 3, we again do we keep on checking the maximum of two values and we just provide those values. Now at this O and O there is a match, so this point there is a match, but before that there is no match. So over here again we check the maximum of next adjacent values, so the value becomes 1. Again maximum of adjacent values, the value becomes 1. Over here we see a match, so whenever we see a match we do 1 plus diagonal. So 1 plus diagonal is actually 2, which means we can just put the value 2 over here. Now since we have 2 over here, this would become actually the maximum of adjacents because there is a mismatch between R and O. So maximum of adjacents is 2, and again the maximum of adjacents between these two values is 2. So at the end we just find the maximum value and that is 2. And see our solution, how beautiful it looks. We were able to calculate everything because we had this original initial case. Using this initial case we were able to compute all the values, and over here because we had like these ends matching, we were able to get 1 because 1 plus diagonal. But even if this was not a match, this was something else, basically we could have filled this value with 0 as well, and then again we will subsequently move forward with our solution. I hope that this this dynamic programming solution makes sense. You are able to understand that how we come up with, why we created this additional column and row, and treating them as a base case, we start filling up our matrix. And basically this problem was originally NP hard problem. What NP hard means is that the problem is runs in non-polynomial time, but using the smartness of computer and because we are storing the values and we are keeping track of it, we are actually able to solve it in n times m time complexity. So even for dynamic programming approach, the time complexity would be big O of n times m, and the space complexity would also be big O of n times m, because we need to create an additional matrix to store all these values. So first of all we'll create a matrix to store the values. Now we will create two loops to iterate over the matrix. We will start at the bottom right position and eventually we will end up at the 0 0 position. So now inside the loop we have two conditions. First condition is if both values are matching. So if both values matches, we need to do 1 plus diagonal. So okay, now we have taken care of one case. Second case is that both values are different. So if both values are different, for matrix of I and j would be we need to select the maximum value out of the adjacent values. And yeah, I think this should be it. This should be our logic. And let's try to return the position, return whatever value we found at the first position. And let's try to run the code. Okay, as expected, there are some errors. Oh, okay, our solution seems to be working. Let's try to submit this. And yeah, our solution works pretty fast. It is comparing to other, it's pretty faster. Hello friends, we are still not employed by FAANG company, so let's not stop lead coding till we get there. Today we are going to do a very important lead code medium problem, word break. Let's understand the problem statement. So basically we are given a string s and we are also given a dictionary of string word dict, and we need to return true if s can be segmented by all the words that are given inside the word dict. So if we look at the example, suppose our s is lead code and the word dict we are given is first set is lead and second set is code. We can clearly see that this lead code we can generate from whatever the values we are given in this dictionary, so we will return true in this case. And we are also mentioned that we can use the same word multiple times. So suppose if this problem was lead code code something like this, we would still return true because or whatever words are, we can still make it through this dictionary. But if we were given some wording like this, that lead code lee, so up until this point we have the words that we can make from this dictionary. The thing is, this lee, there is not a specific word given for that. The word we are given in the word dictionary is lead, so it does not match. So in that scenario we would return false, otherwise we would return true. Okay, let's try to understand that what would be the brute force approach. Suppose we are given s is equal to espn and the dictionary we are given is e, sp and n. So we can clearly see that all the words are present in the word dictionary, so the answer should be true. And in the brute force solution we are going to use a bottom up approach. So and in this video I'm going to show bottom up approach all the way, even for the optimal solution. So this can also be solved as a top down approach, so let me know if you want to make a separate video on that. And there is also one more thing to consider. Suppose we are given something like s is equal to null value or empty string, and in the word dictionary we are given some elements like a b blah blah blah. So this case we can clearly return as true. Why? Because this empty element will always be there, though it might not be showing. But the thing is, if there are no elements in our given string, we can always return true because the emptiness is also exists in this word dictionary. So we are going to use this logic, and let's see that how we can build our brute force. So we are doing bottom up, so we are starting from the lowest value and eventually we are going to make the whole world. So the first value we need to, so we are at the 0th position. The first value we need to make is simply the word break of a value e, and the word break of value e is very easy to calculate. We only need to check that whether the word break of empty string and the value e exist in this given word dictionary or not. So basically, and we know that if there is an empty string scenario, this will always be true because I just explained it to you how. So we only need to see that whether this E exists in this word dictionary or not. If this exists, we can clearly say that this is true, and we can denote the value of word break of E as true. Now the second decision we can make over here would be to see the word break of two elements, so E and S. And how can we determine the word break of E and S? Well, again, it's simple. So we have two ways to determine that. Either we can do a word break of empty string, and we can check that whether this ES value is present in this word dictionary or not, or we can do a word break of value E, because we know that this is always true. The word break of empty is always true, so we can do a word break of E, and we can check that whether the value S is present in this given word dictionary or not. And word break of E, we already know how to do it. For this word break of E, we need to do word break of empty, and we need to calculate the value of to see that whether this E is present or not. The third option over here we can have is and you guessed it correctly, the word break of three elements, so ESP. And for this three elements we again have three more possibilities, so word break of empty string, and we need to check that whether ESP, all these three exist in this scenario, or we need to check that whether the word break of this E and SP exist, and the word break of ES and P exist. And yeah, so these are the three ways we can determine that whether the word break of ESP exists. The next option we have is the final scenario, that whether the word break of ESPN exists or not. And to check that, we will have four possibilities. So first one is that we check the empty string, and we check whether the ESPN, the whole word, is present in this word dictionary or not. Or we can check that whether the word break of E is present and SPN, these three values are present or not. Or we can check that word break of ES is present, and we can check for PN. Or we can check word break of ESP, and we can check the value N. So these would be the four cases where we need to calculate all of these, and for every single one of them. So even in order to calculate this word break of E, we will use this method. To calculate this word break of ES, we will calculate this whole method. And yeah, so this would be the brute force solution. Eventually we would find that whether we are able to make this ESPN or not, and whatever result we get, we just need to bring it upwards, and we would be able to find the solution. So this solution works, but it works in a very horrible way, because at every single location we have two possibilities to make, whether we want to keep that element or not, and our decision tree keeps on growing and growing and growing. And though we will come to the correct solution, but it's gonna take us a lot of iterations to achieve that, because over here you can see that we only had these four elements that we need to consider. We generated such a big tree, and over here most of the values we did not even completed the whole sub iteration for them, because I would be running out of space. So the time complexity, as you have guessed correctly, for this approach is actually big O of 2 to the power n, because at every single location we are making two decisions, which is pretty bad. And why it is 2 to the power n? Because we are calculating everything at the same time. So see that, do we have a room where we can save whatever we have calculated before, and can we use it further down the road? Of course we can, because notice over here this word break of E, we are using it over here, but we have already calculated its value. So why do we need to calculate its value again over here? Same goes with this word break of ES. We have already calculated the value over here. So why are we repeating this whole process? There are a lot of repeated effort. This is repeated, this is repeated, this is repeated. We have already calculated all these values. So somehow if we just create a cache, we store that whatever the values we have calculated so far, and keep track of that cache, and whenever we need to encounter that whatever value we are calculating right now, we can simply check that whether that has already been calculated, and using that we can actually come up to a better solution. since you guessed it correctly, that because we are using something that we have already calculated in past, we are keeping a track of it in some form, and we are using it further down in our next iterations. So basically we are using the most beautiful thing in the computer programming, the dynamic programming approach. In the dynamic programming, we are going to create a single array of size whatever the given input string is, and based on that particular array we will calculate all the values that have been calculated so far. And because this is a bottom up approach, we are going to start filling up array from the 0th position, and we will reach at the end, and in the end, after all the calculation, we will just simply return whatever the value we have calculated over here. So let's see that what would be the optimal solution. Suppose again we are considering the same example. S is equal to ESPN, and the word we are given is ESP and N. And now let's create a new data structure called DP of an array that is of size 4, and there would be, so 0 1 2 3 4. Now we know that this 0th position would always be true. And why it would be true? Because this indicates that for DP of size 0, which means that for string of size 0, does the word dictionary contains this particular element or not? This is what this DP is representing, that at every single location, whether the value of that length of the character, is it present in this word dictionary or not. So DP of 0, we know that that's an empty string, and if it is an empty string, we can determine the value as true. So this would become our base case, and this is very important to identify in a dynamic programming problem, that we need to have a base case. And initially we would set up all the other values as false, and we will run our iteration. So let's see that what each of these values are going to represent. And you guessed it correctly, that this value represents a word break of 0. This represents the word break of 1. So in this case it would be the value E. This represents the word break of value ES. This represents the word break of value ESP. And this one represents the whole word, so word break of the value ESPN. And yeah, so at the end, whatever result we find over here, if we just return that, that would be our perfect solution. So example we are going to take is the same one that we have been discussing. So the S is ESPN, and the value of word is ESP and N. And we know that our dynamic programming of value 0, this is our base case, that is true. So what we are going to do is, we are going to iterate over, starting from single element, we are going to keep on increasing the size of our element. Depending on the size of our element, we are going to fill up this DP array, and at the end we will just return the value. So initially we will calculate just for value E. So DP of 1 would be calculating the word break for value E. So let's see that whether this value E is present in this word dictionary or not. So the value is present, so we can say that the DP of 1 is true. Okay, this is good. Now let's check for the second element. So for DP of E2, this would be calculating the word break for ES. Now we know that we can break down this word break for ES in two parts. Either we can do like an empty string, and we can check for this value ES, or we can do the word break for the value E, and we can check for the value S in this given word dictionary. If we go for this one, ES is not present over here, so we are left with the second approach. In the second approach, we know that word break of E, which means this DP of 1. So DP of 1 is already true, so we can say that okay, this is true. Now we only need to check that whether this S is present or not. So S directly is not present in this word dictionary, which means that this condition is not satisfied, this condition is not satisfied. So we can say that the value for dp of 2 is actually false. So we will just mention it over here that this is false. Okay, let's try to calculate the dp of 3. So dp of 3 means word break of elements ESP. Word break of ESP means three things. First one is that we can directly calculate to see that if ESP is present or not. This is not present, so this condition won't work. Second one is we can check that whether the word break of E is present and the word SP is present or not. And third we can check is whether that word break of ES is true and the P is present. Now the thing is, we already know that this condition is not true. The ESP is not present, which means we need to check these two conditions. Now let's check this bottom condition first. So word break of ES, this word break of ES is actually in the dynamic programming array, it's the second position. So dp of 2, we need, so dp of 2 and the value p. Now we know that dp of 2 is already false, which means that this condition will also be false. So we don't even need to calculate, and we don't even need to check for this element p in the word dictionary, because we know that since this dp of 2 is false, we can just ignore this case and let's focus on this one. So word break of E, which means that dp of 1, so dp of 1 is true. If dp of 1 is true, which means that at least this condition is true. Now we need to check that whether SP exists in the word dictionary or not, and SP also exists in the word dictionary, which means that dp of 3, we can consider this as true. Let me also put this one on this side. Now let's calculate the dp of 4, which means word break of ESPN. So again, this will have 4 conditions. Now I'm going to write this in a different manner. So we can also say that this is dp of 2 and pn, because dp of 2 represents this ES, and we can also say this as dp of 3 and n. And yeah, these are the 4 conditions we need to check, and if any of them are true, we need to return true over here. So let's check the first one. Does ESPN exist in over here? No, it does not, so this is false. So WB of E is true, so at least one is true, but SPN does not exist over here, which means this is also false. Now DP of 2, this is already false, which means we don't even need to calculate and check for this PN. Now the last one is DP of 3. DP of 3 is true, so this is good. Now we need to check whether N exists over here or not. So N exists over here, which means this is true. So we find one case that is true, so which means that over here we can mark this value as true. And remember that this given string, this is of length 4. So because this is of length 4, we simply need to return whatever value we find as dp of 4, and that is true. So in this scenario, we'll just return the answer as true, and that would be our solution. This is a very good solution, because notice that we are already calculating what we need so far. We are keeping track of it at every single position. Because we have calculated these values, we are able to use it effectively and come up to the result. Let's calculate the time complexity. So we are iterating over all the elements at least once, so that is an n. Then we are also creating substrings. So for every value n, there can be n minus 1 substrings, which means that we need to do additional n work. So the time complexity would be big O of n cube. So this is also pretty high time complexity, but if you compare it with 2 to the power of n, this is actually way lesser. Because this time complexity, that can still be calculated, and this is a polynomial time complexity. But the thing is, this one is exponential, and yeah, we need exponential salary but not exponential time complexity. So let's code up the solution. Okay, let's create a boolean array to store our cache, and we'll name it as dp. We'll assign its length to s.length plus 1, and we know the base case where dp of 0 would always be true. Also, for this word dictionary, this is a list, so we are going to create a hash set that will store the strings, and we will store this word dictionary over there, so it becomes faster for us to access the word dictionary. We'll just name it word set. Now I think we are all set to start our loop, so we'll create the two loops. Notice we are starting our loop from I equal to 1 because we don't need to, we already have the value for I equal to 0. And we are going to start the second loop from 0th position, and while j is less than I, because we only need to go up to ith point. Now inside the loop, first of all we will check that whether the dynamic programming for the jth value exists or not, and this is what I already explained in the solution explanation, that if this is true, then only we check that whether the word set contains the substring. So we'll use a substring method, and we'll provide the parameter as j and I, because j is less than I. And if this is true, basically we just need to assign the value of dp of I as true. And yeah, I think that's it, and we don't need to do anything. And at the end of the loop, we can simply return the value of our dp of s dot length. And yeah, also when we find this value dp of I is equal to true, which means that we can break out of this inner loop, because there won't be another pair that we need to calculate, because even at any moment if we find a single true, that's sufficient for us. So let's try to run this code. Okay, looks like our solution is working. Let's try to submit this. Yeah, our solution works. It is accepted by LeetCode, but notice that this solution is actually pretty slow. It is taking a lot of time, and it is not as fast as our other solutions. So there is one trick we can do is, rather than going from from j equal to 0 to I, we can actually go in reverse. So we can start the position of j equal to I minus 1, and we can see that whether j is greater than or equal to 0, and we will do j minus minus. That way we would be able to find this a little bit faster. So let's try to run the code first. Yeah, this works. Let's try to submit it and see the significant difference. Now our solution is much faster, and even if you see over here, previously this one was running in 13 milliseconds, and this one is now runs in 4 milliseconds. Basically we are just eliminating and breaking out of this inner loop faster. We are not doing anything special. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do a very important lead code problem, and I have provided the introduction of what are the things to expect from this video. We are going to solve the combination sum problem, and first of all I'll be showing that what are the top companies that have recently asked this question from Lead Code Premium. We'll understand the problem statement. We'll also find the optimal solution, and we will also determine that what would be the intuition behind it. We will create an example and we'll walk through it, and at the end I'm going to write a Java code. I'm going to explain it thoroughly, that how we come up to it, and also we would be explaining the time and space complexity. So first of all, these are the top companies that have asked this problem recently, and if we see from past 6 months to a year, it's eBay, Google, Goldman Sachs, and these companies. And pretty recently, Amazon has asked this question 20 times in its interviews. Facebook has asked this question 18 times in its interviews. So I highly suggest you to take a look at this problem, understand it completely, and then practice it as much as you can. This is a medium problem, and we are given a distinct integer called candidates, and we are also given a target integer, and we need to return all the unique combinations of candidates where we can reach up to the target value. Now this is a little bit tricky part to find all the unique combinations for this target candidate, because let's try to understand this with an example. So over here we are given the candidates as 2, 3, 6 and 7, and we need to reach the value number 7. So we can clearly see that 7 is already present over here, so we can return this one. The thing is, we need to return all the unique combinations. So one unique combination is 7, second unique combination, and also one more thing, we can use the same number from the candidate unlimited times. So if we apply this theory, then we can find another value that can reach to the sum of 7, and that would be 2 plus 2 plus 3. If we do that, this also sums up to 7. So we need to return a list where the two values are 2, 2 and 3, and the second element is just 7, and this would be our solution for this given problem. Okay, let's try to understand this problem with a custom example. And it is really important to create your own custom examples, because it shows that you have the ability to think outside of the box, and you can create test cases on your own. It is a really important skill to have for any engineer, and especially FAANG engineers. So we are given 3 candidates, 2, 5 and 6, and we need to see that what are all the combinations we can get out of these candidates to achieve the target value 8. Now just by looking at it, we know that the two combinations we can create is 2, 2, 2, 2. This is one combination, and the second combination we can create is 2, 6, and this would be our answer. The thing is, let's see that what would be the most basic solution we can come up with, and what would be the intuition behind it, and based on that we would be able to create an algorithm that would solve this problem. So initially we are at this position 0. Now at this position 0 we have 3 possibilities from which direction we can go. We can either go to this value number 2, we can go to the value number 5, or we can go to the value number 6, because these are the 3 candidates that we are given. And also we should not forget that the target value we want to achieve is 8. Okay, so keeping this in mind, we need to go and pick a side where we need to go further, and keep going. So again, let's just go on one direction for all the cases we can. So over here we are at 2. Now remember that we can use same element infinite times, which means that there can be one possibility as 2, 2. Of course, there can also be one possibility as 2, 2, 2. Of course, the thing is, notice that we need to put a constraint for the number of decisions we are making, and the constraint is that if at any point the direction where we are fetching all the candidates, if the sum of those can either be less than target, they can either be equal to target, or they can be greater than target. These are the 3 possibilities we can have. If it is less than target, which means that there is still room for us to find the potential combination, which means we can keep further going on that direction. If we are already at value number 8, or whatever target we are, we can directly put this value in the result. But if we and which means that we have found the combination, so there is no point in going further after we have already found the combination, because all the elements, they are only going to add up to whatever combination we have, which means that we won't be able to find another combination with the same numbers that were used to achieve this equal to. And the third option is that the value could be greater than 8. If it is greater than 8, why are we keep on going or to do more iterations and putting more strain in our computer? There is no point in doing it, because we could have infinite options, and if we do it, this would be like the best way to deplete the resources of our company. So we don't want to do that. So now, since we have kept these things in our mind, now let's see that how can we use them over here. So far the sum we have found up until this point is only 2. But the thing is, over here we have 2 candidates, and the sum we have found so far is 4, which is still less than 8. This is 6, again still less than 8. Now over here we can have one more possibility as 2, 2, 2 and 2, and if we do the sum of this, this is 8, which means that this is actually equal to whatever the target value we had. So we can add this to our result combination. We would have that we have already find one value in our result, and we will just add it as 2, 2, 2, 2. This is one combination that we have found so far. The thing is, we are not done yet because we still have other candidates that we need to look at, and we need to check the possibilities. The thing is, we have concluded at least one thing so far, and that thing is we can't go further down on this path because all the values would be greater than 8, and which is not what we want. So the only way we can go is actually we can go back and see that have we missed out on any combination. So over here the next possibility we can get is we have already used 2 as our candidate for this value 2, 2, 2. So the next possibility we can have over here is it could be 2, 2, 2 and 5, or it can be 2, 2, 2 and 6. So let's do sum of all the combinations. So some of these combinations would be 11, and some of these combinations would be 12. Notice that both are actually greater than the value of our target, which means that we can't go further down at any of these positions, and we have exhausted all the possibilities up until this point. So since we have already exhausted the possibilities up until this point, the only way we can go is we can go back. At this position 2, we have exhausted all the possibilities there can have. One, we found the answer, and the other two we found that it cannot be part of the combination, which means that we have already exhausted all the possibilities for this value 2 to 2 as well, which means that we can't go down but we can go up. So over here, have we exhausted all the possibilities so far? No, there are still room, there are still other possibilities that we can check. So let's do that. So one possibility we can have over here is 2, 2, 2, which we already checked. The next possibility could be 2, 2, 5, and the next possibility would be 2, 2, 6. So sum of these values is actually 9, and sum of these values is actually 10. Again, both are greater than whatever the target value we had, which means that we cannot go down. So we will go back. We went back. Over here we check that we went through all the possibilities, which means that we are done over here. So we can't go down any further on this path, but we can go up. So if we go up, we ask ourselves a question that have we explored all the possibilities at this position? No. The possibilities we could have is 2, 5, 2, 6. So let's take this value first. So at 2, 5, the current sum we have is 7. 7 is less than whatever value we have as our target, which means that we still have possibilities. The possibilities we can have is 2, 5, 5, or 2, 5, 6. Notice that over here we only had 2 possibilities where we can calculate it from. We did not had the possibility of 2, 2, 5. Why? Because we already calculated it for this portion over here. Remember, in the previous iteration we already calculated for this scenario, which also shows one very important property, and their property is that out of our candidates, whatever the candidates we are given, if we are at any particular position or any combination of positions, so whatever value we have as last, we can only use that multiple times, or we can use the values that come after it. We cannot go backwards because we have already exhausted those possibilities in an iteration before this, as I showed you earlier, that this we have already explored over here, and this 2 to the 5 2, 5 we are exploring at this position 2, which means that the only combinations we can make up after this point is either 2, 5, 5, 5, something blah blah blah, or 2, 5, 6, 6, 6, something like this. But we can't make like 2, 2, 2, 5 because we already checked that over here. So and this is a very important property that we are going to use. Okay, at this point the sum we can have is 12, which is greater than 8, so we can terminate over here. We can't go down any further. And over here the sum would be 13. Again we can terminate over here. We can't go down, which means we have to go back. So we come back at 2 5. We say that okay, we have explored all the possibilities over here. We go back to value number 2. Now the thing is, at value number 2, have we explored all the possibilities? No, there is still one possibility pending, which is 2 6. So at 2 6, this value, the sum would be 8. Again, this is really critical because we have found a pair that equals to whatever target value we had, which means that we will add this combination to our result list. So over here we will add another entry 2 6, and after adding this, we have explored all the possibilities after this point, which means that we would go back. Now at this position 2, we have explored all the possibilities it could have, and because we have explored it, we will again go back to our 0th position. The thing is, we are still at 0th position, so can we stop now? No, we can't stop because we still have a whole lot of possibilities that we haven't touched so far. Because remember, over here we still have this 5 and 6 pending. So let's see that what could be the possibilities over here. Now at 5, again we can only have two possibilities. As explained earlier, we could have either 5 5 or we could have 5 6. So let's do the sum of these values. So 5 5, the sum is actually 10, and 5 6, the sum is 11. Both are greater than 8, which means that we can terminate over here. So that concludes that at this position 5 we ran out of the possibilities. We went up. At this position we are done. So again we go back. At 0th position. We check that do we have any other options where we can explore, and yes, currently we are at value number 6. So 6 is again less than our target 8, so we can go further from 6. The thing is, at 6 we can only do 6 6. We can't do any other combination because those we have already checked so far, which means that 6 6, the value is 12. So 12 is already greater than 8, which means that we can't go further from this, which means we can't go further. We go back. At 6 we see that have we explored all the possibilities? Yes, we have explored all the possibilities, which means again we go back to this position 0. So at this position 0, we check that now have we explored all the possibilities? Yes, initially we check all the possibilities for the value 2, again we check for value 5, and again we check for value number 6, which means that even at 0th position we are done. So our base case has satisfied. Now whatever we have stored in our result result list so far, we can simply return this, and this would be our final solution. And this is actually the optimal solution that we can achieve. Notice over here that we are doing lot of repetitive work. At any position we were calculating the different possibilities we can have. We were picking a possibility, we are exploring in that direction, depth first search. We kept on exploring. Once we found a terminating case, we would go back to a point where we can still explore for more possibilities. Over here again we would further go down to additional possibilities. We would find a terminating case, again we would come back, and eventually we would come back to the 0th position from where we started, and after the calculation we will return our result. So this, where at any point we are coming back from where we originally started. This is actually called backtracking. This is a really important concept in computer programming, and I just showed you that how can we use it, and that is why, because this concept is really important, it has a lot of very practical applications, and that's why you see that why all those big companies like Google, Facebook, Amazon, Goldman Sachs, they were interested in asking this question to their candidates, because they want to know that are you familiarized with very important things that are really critical and can you go down that path? And yeah, so since we have found our optimal solution, I did not mention explicitly that I was showing you the optimal solution, but the thing is, I told you that this is the intuition behind it. And once we knew the intuition, we just need to find a way to implement it in computer programming. The way to implement this, you must have guessed it correctly, that we were doing so much repetitive work again and again, and we were using it somewhere, and we had some terminating conditions that either if the value is equal to or greater than our target, we would terminate, which means that we were using recursion at its best over here. So yeah, this is basically our solution. So let's calculate the time and space complexity. That time complexity for this one would be big O of n to the power t. Now first let's determine that what this n and t means. N is actually the number of candidates and the least value for this one, and t is actually the total amount. Because imagine that what could be the longest sequence we can have at any given position. Well, suppose our target value is 8 and our candidate is 1, which means that we would do 1 plus 1 plus 1 up until 8 times till we get the value 8, which means that we need to go in one direction 8 times, and at any position we can have multiple options or we can make multiple decisions, and from further down we can go ahead, which means that we need to do this work n to the power t times until we find the solution. So that's why this is the time complexity. So first of all, we'll create our result list, and now we'll create a list to store the current combination. Okay, now we'll create a backtrack method, and in this would be our recursive method. So initially we are going to provide the target result combination 0 as the starting point and the candidates array, and after whatever the result we get back from that recursive call, we simply need to return whatever we find in this result list. So let's create the recursion method. Okay, so first of all we are going to create the terminating cases. So if target is equal to 0, which means that we have find a combination that sums up to the target value, so we can just simply return it to we can simply add the combination to our result. If this is not the case, we need to return we need to check that whether the target is less than 0, which means that we have already surpassed our target and we need to break, so we can just return null. If both cases are not true, which means we still need to look for our combination. So we'll start by checking in our combination from the position start, and we'll go until we still have candidates. Now inside the loop, first of all, we will add whatever candidate we are currently looking for in our combination list. Okay, after that we can do our recursive call, and as a target we will have target minus whatever candidate value we found. and start would be ith position. And I think that would be it. Yeah, one more thing, we will have to remove the entry from our combination list because we will be doing backtracking when we move towards the next value. And I think this would be it. Let's try to run the code. This should have worked, but I don't know why it's not working, so we'll just enter the value manually. Oh, it should be candidates. Okay, our solution seems to be working. Let's try to submit the code. And yeah, our solution works perfectly fine. And hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do a very important lead code problem, Decode Ways, and this problem has been asked in a bunch of different FAANG companies like Amazon, Google, Facebook, Microsoft, Uber, Lyft, Apple. So I highly recommend that you focus full attention to this problem. This is the breakdown that we are going to do for this problem. We are simply going to understand the problem first. We are going to see a brute force solution. Based on the brute force solution, we are going to see that how can we create an optimal solution, and eventually we will write the Java code for that. And this is a lead code medium problem, and we are given a note that basically a message containing letters can be encoded into numbers using the following method. So A is 1, B is 2, and up until that, if we keep doing that, Z is actually 26. And we are given a string of S that contains digits, and we need to return the number of different ways we can decode it. So let's understand this with an example. Suppose our given input S is equal to 12. We can decode this in two ways. So one way to decode this would be to consider 1 and 2 as separate elements, and 12 by itself as a single digit. So this the value for 1 and 2 would become A and B using this logic, and the value of 12 would become the letter L. So we don't need to return these values, we don't care about them. The thing is, we need to return that how many different ways we are decoding this given input string, and in this case the answer would be 2. Let's take another example. So suppose our given input S is equal to 226. How many times, how many different ways we can decode this one? So one way to decode this one is 2 and 26. So that's one way. And second way to decode this one is 2 and 6. So that is second way. And the third way to decode this one, 22 and 6. And if we check out the values, so this would becomes B Z, this would becomes B B F, and this would become V F. So over here we can see that there are three ways we are decoding this given string. So in the answer we will return the value as 3. Now let's consider one more case. Suppose the value 0 would be a special case, and there could be multiple possibilities where 0 can appear. So suppose our given input S is something like 0 1 1. So in this case we won't be decoded in any manner, because remember that our range starts from this value number 1 up until 26. So 0 is not part of the range, so we cannot begin our string with value 0 at the beginning. So this won't work. Second possibility, that 0 could be somewhere in the middle. So suppose our given input S is equal to 1 0 1, something like this. So in this case we cannot decode this in 1 and 0 1. We can't do this. Why? Because we can't decode this 0 1, because remember that in this scenario, if 0 comes at the beginning, we can't decode it. The way we can decode this is we can consider this as 10 and this as 1. Yes, that value of 0 can appear at the end. So our input string S can be something like 2 0 0. So in this case we can decode this value 20, but we can't decode this 0, so we won't be able to return anything. Or our value S can be 5 2 0. So in this case we can decode this. We can decode this value 5 and we can decode this value 20, because 20 is again between 1 to 26. But if we are given something s is equal to like 570, we can't decode this, because we can decode this 5, but we can't decode 70, because 70 is not part of this 1 to 26 range. So when value 0 comes in, it becomes a little bit tricky and we have to just take care of it. For brute force approach, let's take a custom example. Suppose our given s is equal to 2, 1, 2, 3, and we need to see that how many different ways we can decode this one. So brute force approach is pretty simple. We just take all the possibilities starting from the first value and keep moving and keep building our solution, and when we reach at the end at any given path, we consider it as a one way to decode it. So initially we can decode this as 2 and whatever the remaining value 1, 2, 3. We can decode this further into 2, 1 and whatever value remaining. Again same thing, 2, 1, 2 and this 3, and in the end we can decode this as 2, 1, 2, 3. So this would be one way we would be able to decode this. So where if we treat all the values as separate entities. Now let's go back and see that can we have more possibilities. So over here we cannot have any more possibilities, because this 2, 1 and 2 are already being decoded, and this 3 we only have one possibility to decode it by itself. So we don't have any possibility over here. So we go back further up. Do we have any possibility over here? So yes, over here we still have possibility that we can decode this 2 and 1 the same way we have decoded over here, but this 23 we can decode it as a single value. So of course we reach at the end of the loop. So this is one more possibility on how we can decode it. Now let's go back. So for this value 123, of course we still have more possibilities, because over here we are considering this value as 2 and 1 separately. So over here we will consider this as 2 as already being decoded, and rather than considering this as 1 as separate character, we can also consider it as 1, 2, and then we can decode 3. So this can also be another way. So we'll just mark it. Okay, now we have exhausted all the possibilities over here. Considering this value, if we start from this value number 2, so we come back at our main point, and let's see that what are the more possibilities we can have over here. So we can do, rather than choosing 2, we can choose 2, 1 and whatever the remaining stream. So remaining is 23. Okay, now let's see that how many different possibilities we can have over here. So we can have two possibilities now. We can do like 21, 2 and 3. So that is one option. Or we can do 21 and 23. So that is second option. And yeah, both would be a separate ways. And apart from these, we cannot make any other possibilities. So essentially we are we can say that there are 5 different ways to decode this 2, 1, 2, 3 string, and those 5 ways are mentioned over here. What is the problem with this brute force approach? Well, the problem with brute force approach is that actually we are doing a lot of repetitive work. How we are doing repetitive work? If you notice over here that we know that we need to calculate that for this 23, how many different ways we can compute this one. But this 23, we have already computed it over here. So since we have already computed it over here, it is not very fruitful to compute the same thing twice. And in brute force we are not doing it. So that is why our path will keep on growing and growing until we reach to our all the possibilities, which means that we are actually doing exponential work for this brute force approach. So of course the time complexity would be big O of 2 to the power n, which is really bad, and we should avoid it in all cases. And actually it can be avoided pretty simply. If we just use memorization, if we just create an additional data structure, something like an array or something, where we store the value of calculations that we have already done, and if we at any point come back to the same calculation that we have already computed, we can simply return that value. So we can use something like an array or hash map. I think hash map would be more efficient in this case because we are able to look up things in constant time. And if we only apply that, we can actually implement this solution, this brute force solution, in very effective manner. We can actually use recursion because remember, at every single moment we are repeating a sub problem. So we are repeating a sub problem and we are computing that. So if we just use memorization with recursion, so for this approach, we can actually achieve the answer in time complexity of big O of n rather than this 2 to the power n, and that would be really efficient. Okay, before I go into the optimal solution, I want to show you a few observations. Suppose our given input s is equal to 7. So how many different ways we can decode it? Of course, only one way, we can just use 7. Suppose our input is 7 7. We can still only decode it one way using like 7 7, and that would be the only way we would be able to decode it. Even if our value is 7 7 7 7 7 7 7, whatever the value we have, all of these can only be decoded just one way, because all of these values, they are forming a value where we can only use individual characters. Now, what is the scenario where we can use the characters that are not individual and we can collectively use the pair of elements? Okay, now let's take one more example. S is equal to 2 1 2 3. And now let's try to see that how many different ways we can decode this one. This is the same one we have used in our brute force approach. So we know that there are 5 different ways we can decode this one. But the thing is, we are going to do things a little bit differently over here. We are going to decode all of these values. So first we'll start with value number 2. How many different ways to decode this one? Only one way, and that way is 2. Now let's consider the second value, 21. How many different ways to decode this one? Well, of course, two values, two different ways, and those ways are 2 1, so that is one way, and second one is 21 by itself. And let's take the third value, 2 1 2. So there are actually 3 different ways to decode this one. So let's consider the next value as 2 1 2 3. So we know that for this one, there are actually 5 different ways to decode this. And the 5 ways are, okay, you must be thinking that why am I writing all these letters? Because the thing is, there is actually a very important relationship that exists whenever we find out, whenever we add a new value to our calculation, and if that value that is being added, if the previous value of that with that particular value, if that falls between this 10 to 26, actually something interesting happens. So notice over here that this 21 came in. Okay, we are checking for this value number 21. Now the thing is, just for a second, imagine if this value was actually 27. So how many different ways would we be able to decode this one? Well, only one different way, and that one different way would be 2 and 7. So treating both values as separate values. Same goes for 28, 29, and any value above. But the thing is, because this value falls between this 10 to 26 portion, we are able to do something interesting. So notice that whatever value we append over here, there will always be one way to decode it. I'm not talking about the value 0. Forget about 0. Apart from 0, if there was any other value, the way to decode it would be to whatever the way we have been decoding the previous value. If we just add that value, then that would be the way to decode it, which is over here. That 2 and 1, we are already decoding it with whatever value we were decoding before, and we were using that way. But the thing is, over here, this 21 by itself falls under this 10 to 26, which means it is a letter by itself. So we are able to add it to our decode list, and that is why we have 2 over here. Okay, but now the interesting part comes in. Okay, now over here, we are adding one more 2, and this 2 falls between the values 10 to 26, because the appending value becomes 12, so this 12 falls between this 10 to 26. Now let's see that how many different ways we are creating the pairs. Actually 2, 1 and 2. This is same from whatever the pair we had before, just one iteration before. Okay, now this 2, 1, we already had a 2, 1 over here, and we are just appending this value 2 over here. So that is also okay, because we can append it, right? So whatever the ways we were decoding before, we are still using those ways. But the thing is, over here something interesting happens, because this 1, 2 by itself is a way to decode. We are actually able to create this 2, 1, 2 pair, which we were not able to generate over here. We are not able, I mean, we are using this 2 over here, but the thing is we are using it for 2, 1, but we can't do anything further than that. We are already also using this 2, 1, 2 over here. And how can we say that we are using this 2, 1, 2 over here? Is because this value is basically 12, falls between 10 to 16. But the thing is, this 2 actually comes from the first value, this one. And why? Because at any given moment we find out that there exists a pair with the new value being added, and that comes between this 10 to 16. We can actually do sum of previous two values that we have calculated so far, and the sum of these two would actually give us the number of different ways we can actually decode this one. If you still don't believe me, let me show you with another example. Let me clean this up a bit. Now over here we are seeing that 5 distinct pairs are being made, and we are adding a value 3 over here, and we know that this pair 23 exists between this 10 to 26. So that is all okay, right? We know all of these stuff. Now let's see that how many different ways we are generating the pair. So one way is 212, and we are just appending 3. This would be the case even if the value was 2129. If the value was 2129, we would still be able to use this way, because apart from this 3, there would be a 9 over here, but that's not the case right now. But the thing is, we would still be do it. And if you look over here, this is the same path we were taking, and we are just adding one more node, so no impact on the number of results. Second pair we are making is actually 21-2, and we are appending 3 over here. Again, that is the case over here, that we already had a 21-2, and we can append 3 over here, so that gets taken out over here. If we had the 21-29, we would be appending 9 over here, so that still remains common. Okay, there are no issues with that. Now next pair over here is 2 and 12. So we also have a 2 and 12 pair, and we are adding a 3 over here, which means that even if we had this 9, we would still be adding 9, and that would be it. We don't care about it. But the thing is, if we had this 9, we won't be able to generate these two pairs, because notice in these two pairs we are actually creating an additional value by the value that has added over here. And if this value was not between this 10 to 26, this value would not be able to be generated. Okay, now the question comes that we have already exhausted all the possibilities over here. So where does these two additional values comes from? Well, actually, if we look above over here, this one is actually 2, 1, right? So we are also using 2, 1, and we are creating a new decode node 23, and we are appending it over here. Also notice over here that this one is 2, 1, and this one is 2, 1. So we are appending a node over here, 23, which means that at any given location, if we want to see that how many times we can decode it, if we know the information of previous two elements, and if we do sum of those, we can actually generate it. So that's why the value for this 2, 1, this can be decoded 2 times. This value 2, 1, 2, this can be decoded 3 times. So for the value 2, 1, 2, 3, actually this 23 falls between 10 to 26. That is okay, that is perfect. If that is the case, we simply do an addition, and if we do an addition and we just find whatever result we have calculated, and we can simply return this. This is a very effective solution. Now what could be the other case? Well, the other case could be that the new value we are adding, that does not fall between this 10 to 26. So suppose over here the new value we are adding, suppose the new value is 2128, something like this. So after adding this new value, this becomes 28. It does not fall between this 10 to 26. Because it does not fall between this 10 to 26, actually we don't need to do addition over here. We simply need to, whatever the route we can make before this element, that would be the only possibility we would be able to decode this one as well. Because that I just showed you over here, that over here I was adding a 9, and because I was adding a 9, I was only able to make the new decode paths for these three elements. I won't be able to generate these two values, and this becomes our recurrence relationship, and this actually becomes our dynamic programming solution. Now let's try to solve this dynamic programming programmatically. We know that we care about the two previous elements. So suppose our given input is like 2 1 2 3. We initialize two values before that as 1 1. Say we have these two as 1 1. Now we check at any given location that whether the value we have, does this value with its previous value, does it fall between this 10 to 26? Okay, in this case this 2 does not fall between 10 to 26. If it does not fall between 2 to 26, we just need to take whatever we had from the previous element. So previous element over here we had 1, so we'll just take 1. Okay, now we have this 1. So again we check with its previous element that whether the value falls between this 10 to 26, the value becomes 21. It falls between this 10 to 26. So we do whatever the previous two elements were, we do sum of it. So the previous one element is 1, and the previous second element, this one is also 1. So we do 1 plus, so we do 1 plus 1. So we can put 2 over here. Now we have new element. This falls between this 10 to 26. That's good. So we do sum of two previous elements. Sum of two previous elements is actually 2 plus 1. So we can put 3 over here. Now we have this 3. Now it creates the value 23, again falls between this. So we can do sum of 2 plus 3, and that becomes 5. And this 5 would be our result. So this is a very important dynamic programming solution. And at any given moment, if we find out that suppose over here we have an value 8. Now this 38 does not fall between this 10 to 26. So it becomes simple that for this pair, the number of ways we can decode this will still be 5, because we'll just take whatever value we have calculated over here. This solution works perfectly fine, and the time complexity for this case would be big O of n, because we only need to do one iteration across all the strings, and the space complexity would in this case would actually be big O of 1. We would be able to complete this in constant space and time, because remember that at any given location we only need to keep track of just two elements. We don't need to keep track of this whole entire array. We just need two starting elements, and we would keep on iterating them over different values. So this is a very good solution. And okay, first of all we'll check that whether the first element is 0 or not. If this is the case, we can simply return 0. Okay, so we will create two parameters, 1 and 2, and we will initialize both to value 1. Let's run a for loop. We'll start the loop from first position, and we will go up until the length of the given string. We are running it from I equal to 1 because we already checked for the 0th position. First of all, we create a value current to keep track of the current element, and now we check that if the current if the new character that we are trying to add, if that is not equal to 0, we can assign the value of 1 to current. Now we also need to check that after we are adding the value at ith position, are we getting the 2-digit value between 10 to 26. So first of all, let's create a new variable called value, and we'll try to calculate the 2-digit value. We check the condition. So if value is greater than or equal to 10 and value is less than or equal to 26, which means we need to update the current value is current plus whatever the value of 2 we had, because remember the value at current we are already adding it as 1. Now we need to update the values of 1 and 2. So 2 would become whatever the value of 1 we had, and 1 would become whatever the value of current we had. And yeah, I think this would be our solution. So at the end of the solution we need to return the value of whatever the current value we had, but since we are initializing current inside, we'll just return the value as 1. And let's try to run the code. Oh, we can initialize the current as 0. Let's try to run the code. Okay, looks like our solution is working. Let's try to submit the code. Okay, our solution works pretty fast and pretty efficiently. Hello friends, we are still not employed by FAANG company, so let's not stop lead coding till we get there. Today we are going to do a very important lead code problem, unique paths, and as you can see that this question has been asked in Google, Facebook, Amazon, Apple, Microsoft, Bloomberg, all huge gigantic IT companies. So I highly urge you not to miss this video and try to understand the problem as thoroughly as possible. This is going to be the framework for the video. We are going to understand the problem. We are also going to find a primitive approach. We are going to find the optimal solution, and we will write a Java code for the optimal solution. This is a lead code medium problem. We are given that there is a robot and an m cross n grid, and robot is initially located on the top left corner. Now robot tries to go to the bottom right corner. So this is the last place where robot wants to reach. And at any given moment robot can only make one move. It can either go down or it can go right at any point in time. No other ways it can make. So in the problem we are given this m and n, and we need to find that how many distinct unique paths can robot take to reach to the bottom right corner or its final destination. So suppose our given m is equal to 3 and n is equal to 2. This is one of the test cases. So if we draw it on the board, it would look like this. This is where the robot is initially, so I'll just mark it as R, and this is the destination that robot wants to reach, the bottom right corner. Now we know we need to find that how many unique paths exist. So let's see that how many unique paths can we make. And at any given moment robot can either go on the right side or down. It cannot make any other steps. So let's see that what are the possibilities. So this is one possibility. So this is one path. I'll just mark it somewhere. Now this is second path. I'll also mark it somewhere. So this is second path. So have we exhausted all possibilities? No, there still exists a third path, and the third path is like this. 1, 2, 1. And apart from these, we cannot make any more paths. So essentially we are exhausting all the possibilities, and we can return that for this given m and n, the number of unique paths can be 3. Now I hope that this makes problem statement more understandable. Over here initially we are given an example of m is equal to 3 and n is equal to 7. And the number of unique paths they get is 28. But the thing is, this would be such a long example, so I'm not going over it. Okay, let's understand this with a custom example. So suppose our m is equal to 3 and n is equal to 3. So we would have a grid that looks like this. Here this is our robot, this is our destination. Now we are going to calculate that in order to reach to any element, how many unique paths we can take. So suppose if we want to reach to this element, how many unique paths we can take? We can only take one unique path, and that would be to take this right step from here. We cannot take any other step. Same goes for this element, that we can only have one unique path, and that would be to take two right steps from here. We cannot reach to this point any other ways. Same happens for these two elements as well, that we can only take one step down or two steps down in order to reach to these two elements. The thing is, there cannot be any other unique path if we want to get here. But the thing is, when we get to this middle points, something interesting happens. And the interesting thing is, suppose we want to reach to this point, how many unique paths we can take? Well, we can take two unique paths. We can take one unique path to reach over here and then over here, or we can take one unique path to reach over here and then again reach over here. So we can say over here we took two unique paths. But the thing is, if we just see that what are the entry points to get to this point, actually there are only two entry points to get to this point. One entry point is that we can, if we somehow get to this point, we just take one step downwards, we come over here. Or if we somehow get to this endpoint, if we take one step on the side, we reach over here. Which means that whatever the unique paths we have at these two locations, if we just sum these two up, it will give us the number of unique paths we can take to get to this point. So let me show you by another example. Now again, let's consider this element. So in order to reach to this element, there are only two ways we can reach to this element. We can either take one step from here, or we can take one step from here, which means that whatever the number of possibilities we have over here, that once we get to this point, we will be able to come to this unique path. Okay, so that is a given. Same goes over here, that no matter how many number of possibilities we have to come to this point, if once we are at here, we are guaranteed that we can come to this point. So in order to reach to this point, the only possible ways are this one and this one. So if we sum these two, we will find the number of unique ways we can reach to this element, and in this case it would be 3. If we continue down the same path for this point, we can take 3 distinct paths to reach over here, and in order to reach to this destination D, we can take 3 plus 3 6 unique paths to get to here, and this actually becomes our answer. Okay, so based on our previous explanation, we know these things. So if we see, now we need to see that how can we use dynamic programming to solve this problem. And the reason we are choosing dynamic programming is because at any single location, we are computing that whatever the previous two results that we have already calculated, and we are using them to calculate the next values. So that pretty much indicates that we need to use dynamic programming over here. Now let's take a 2 by 2 matrix, and we'll just provide the index values. So index values would be 0 1 2 0 1 2, and we would name this matrix as DP to refer dynamic programming. Now the thing is, if we want to find out the value at this position, we know that it would be sum of these two elements. So mathematically we can write them like this, that DP of 1 1, because this is 1 and this is 1, is actually equal to DP of 0 1 that we have already calculated, which is this value, plus DP of 1 0, which is this value, and sum of these two will give us this value. So generically we can actually write them like this, that at any given location, DP of M and N would actually become DP of M minus 1 N plus DP of N and N minus 1. And this would be our recurrence relation for dynamic programming. And I already explained that why are we choosing dynamic programming. And our aim is to find that how many distinct ways we can reach to this destination. So this destination would actually become DP of 2 over here. And if we compare it with whatever M and N is given, this actually becomes the value over here. This would become the DP of M minus 1 and N minus 1. So we start our calculation like this, and eventually we would reach to this point, and we just need to return whatever we have found over here, and this would be our solution. So we can just create two loops. One loop iterate over the column, one loop iterates over the rows, and eventually we will reach to this endpoint. We return this. This becomes our solution, and this is a very efficient dynamic programming solution. Any FAANG companies, Facebook, Google, Amazon, whatever, they would be happy to hire you immediately. So now let's see that what would be the time and space complexity. So time complexity would be big O of m times n, because we need to iterate over this entire grid. So that's why it's big O of m times n. And space complexity, remember that we are creating this additional DP array, which is 2 by 2 matrix, and we are giving the size as m and n. So space complexity would also be big O of m times n, and this would be our solution. Now let's move on to coding. Okay, first of all, we'll create a two-dimensional array and we'll name it as DP, and we'll provide the length as m and n. Now we'll have to create our base case, so we'll fill our two-dimensional array, and this is the way to fill a two-dimensional array. And over here now we'll create two for loops, and we'll start with I is equal to 1 and j is equal to 1, because we already have cases for 0. While I is less than m, I plus plus, j is equal to 1, j is less than n, okay. Now we will provide our recurrence relation. So dp of I and j at any location is equal to dp of I minus 1 j plus dp of I j minus 1. And yeah, this is pretty much it. This should be working. So now let's return dp of m minus 1 and j n minus 1. Let's try to run this code. Oh, it should be arrays.fill, small error. Looks like our solution is working. Let's try to submit the code. Okay, our solution is actually runs in 0 millisecond. It's 100% faster than all the other submissions, which is pretty good. And I'll be posting this in the comments. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do jump game problem. Recently this problem has been asked in Amazon, Facebook, Apple, Google, Oracle, TikTok, all these gigantic companies, and they are some of my dream companies. So I'm going to do my utmost focus for this video, and I hope that you find it enjoyable. This is going to be the framework for the video. First we are going to understand the problem, then we will come up with a brute force approach. We'll improve our brute force approach, we'll find the optimal solution, and then we'll write the Java code for the optimal solution. This is a medium problem, and we are given an integer array nums, and we are initially positioned at the first index, so 0th index. Each element in the array represents that is the maximum jump we can take, and if that is true, can we reach to the last position? So if we are able to reach to the last position, we would return true. If we cannot reach, we will return false. So let's understand this with an example. Suppose our given input is like 2, 3, 1, 1 and 4, and initially we are located at this position. This is the same example over here. So we can see that if we over here, we can take maximum 2 jumps. So either we can take 1 jump and reach over here, or we can take 2 jumps and reach over here. Let's get the greedy approach, and we'll take the maximum amount of jumps. So over here, if we take 2 jumps, we end up over here. Over here, the maximum jump we can take is only 1, so we'll reach over here. Again, the maximum jump we can take is just 1, so we'll reach over here. And this is our last position. So since we have reached over here, which means that we can conclude that we can solve this jump game and we can reach to this end position. So we'll return true in this case. Now let's take one more example. So suppose we are given input like this: 3, 2, 1, 0 and 4. And if we check for the possibility, so over here the maximum number of jumps we can take is 3 jumps. So if we take 3 jumps, we reach at 0. From 0 we can't move anywhere forward. So let's, rather than taking 3 jumps, we'll try to take 2 jumps. So if we take 2 jumps, we end up over here, and over here the maximum we can take is just 1 jump. So again we end up at 0. And lastly, rather than taking 2 jumps from here, we'll just take 1 jump. So we'll end up over here at this position number 2. Now at this 2, the maximum jumps we can take is 2. So again we end up at the 0, which means that in any circumstances, if we start at this position number 1, we cannot reach to this last position. So over here we would return false. This is basically the problem statement. I have given a custom example that we are at any position. We are going to first of all see that what is the maximum jump we can take. We'll try to make that jump. We'll try to see that using that jump, if we can reach to this end index. If we cannot reach to the end index somehow, we will backtrack. We will go back to the position where we initially took the jump from, and we'll try some other possibilities. So let's see that in action. So over here, we are initially at this position number 2. The maximum jump we can take is at value number 2. So that jump will bring us over here. Now over here, the maximum jump we can take is at this position 0, which means that we can't move any further. So we will backtrack. We will come back over here. Now again, we are at this second position. Now let's, rather than taking the 2 jump, we will reduce our jumping possibility and we will just take jump of 1 step. So now we reach at this value number 3. And over here with this value number 3, we can take maximum jump of 3 steps, which means that we can, if we take 3 steps, we will end up over here. So 1, 2, 3. And at this position 2, the maximum number of steps we can take is 2, which means that even if we take 2 steps, we will cross our last entry, which means that in any case, we would be able to reach to this last element and we would return true in this scenario. Now this approach seems sensible on pen and paper because we are dealing with a small number of things, small number of input, and we are able to clearly see that how the pattern is going on. So let's take another example. So these are the values. Let me also denote the index values for these. Now with every single iteration, I'm going to note down the index value transition we are making. Okay, so initially we are at this position number 5. The maximum jump we can take is a 5 step, which means that we would end up over here. So initially we would do something like this. So 0 to 5. This is one step we take. We are at 0 position, which means we can't go forward, which means we have to backtrack, which means that again from 5 we will come back to this 0th index. Now from 5, rather than making a jump of 5 steps, we will make jump of 4 steps and we would end up at this position 4. So from 0 we would end up at this position 4. Now from this 4, the maximum jump we can make is 1. So again we will take 1 step jump and we would end up at this position 5. Again we are at 0, we can't do anything, so we will have to backtrack. So in order to backtrack, we will go back to this position number 4. Again we have to backtrack from this position 4, so we will end up at 0. Again we will, rather than making a jump of 4 step, we'll make a jump of 3 step and we'll end up over here. So we end up over here, and so on and so forth. So you can see that this in this approach, all we are doing is just we are going someplace, we are coming back. Again we are going, and then again we are coming back. Again we are going to some next element, we are going to some next element, and we are coming back. And suppose this keeps repeating multiple times, you are essentially depleting your resources, because if you see the time complexity at any single iteration or at any single value, we have two possibilities: whether we want to keep this value in our current transition, or we do not want to keep our value, keep this value in our current path that we are calculating. Which means that the input, if we make decision tree, the decision tree would keep on growing and growing with addition of every single value. Which means that we are basically making a lot of decisions, and the time complexity in this scenario would actually be big O of 2 to the power n, because at every single position we are making two possibilities. This is a very bad exponential time complexity which we cannot allow in any scenario. Okay, so the issue in the brute force approach we had is that we were doing a lot of repetitive work, because at any point we found out that we are not able to make any progress from this point. We were still ending up at that point. So let's see that how can we counter that with a better approach. Suppose we create an additional data structure over here. So we create a dynamic programmatically additional data structure over here. Let's create an array, and in that array we are going to define that at any position can we reach to this endpoint. And if we identify that yes, we can reach to this endpoint, we would basically fill that position as true. And let's see that how it can help us. So if at any point in time we are at this final position, we know that this is the main terminating case, which means that we can put true over here. So this final element we can always put true, and this would actually become our base case. Now we have a base case. We are going to start iterating on from right to left manner, and we are going to start filling up our DP array to see. And in the DP array, the only thing we are mentioning is that at any given location, if we are able to reach to this endpoint or not. If we can, we'll just mark it as true, otherwise we'll mark it as false. Okay, so now one step over here, this is this value has potential to make two jumps, and it only takes one jump to get to this last point, which means that if we end up at this fourth position, we can reach to this fifth position, which is what we want. So over here we can also fill this as true. Now we are at this 0th position. From the 0th position, can we reach to this fifth position? No, because we can basically can't make any jumps. So we'll just fill this as false. Okay, now from this one, can we end up at this fifth position? So we are going to, now the interesting part comes. Now we are going to check that, okay, this has possibility of only doing one jump, right? So with one jump, we can only end up at this third index. Now we only need to check that in this DP array for this third index, if the value is true or false. So in this case, this is already false, which means that the maximum we can get to is this third place. From this third place, we can't go anywhere. So we don't even need to check these values. We can only check this DP table, and we can conclude that no, we can't go anywhere forward. So we will put a false over here as well. Now we are at this third position. Now from this third position, we will again do the same check. But the thing is, this has potential to do 3 jumps. Okay, so let's do one jump at a time. So first we take a jump. If we take a jump of one step, we end up over here. We check over here that this is false, which means that this is false, right? Now we take second jump. With the second jump, we end up at this third position. We check in this DP array. This is also false, which means that we can't do anything. Now from this third position, we still have one more possibility, that we can take a jump of 3 values. So if we take a jump of 3 values, we end up at this position, value number, this index number 4. So for this index number 4, we see that the value is true. If we find any true, which means that we can say that from this second, this index number 1, we can reach to this last endpoint. And now for this position, we need to check that it has potential to do 2 jumps. We will only check for one jump. So with one jump, we will end up at this first index. That one is true, which means that we can fill true over here as well. And in the end, we just need to return whatever of DP of 0 we found. So in this case, we can determine that this is true, which means that we are able to come to final endpoint. So this solution is very good. It works perfectly fine. Okay, so the time and space complexity for this approach would be, so the time complexity would be big O of n square, because notice that we need to do one iteration to go on for every single element, and sometimes for any given element we might have to do multiple jumps like we did in this case of 3. So in the worst case we might have to solve this in big O of n square time, and the space complexity would also be big O of n, because we are creating this additional DP array. Now this is still much better than our brute force approach, but our aim is to go into companies like Google, Facebook, Amazon, Apple, and whatnot. So those companies expect the best out of the best solutions. And is this the best out of the best solutions we can do? Actually, no, there is still a better optimal solution, and let me show you how we can get there. Okay, and this optimal solution is actually based on the dynamic programming solution that we just saw. So in dynamic programming, what we are doing is we are creating an additional DP array, and we are storing that whether we can reach to this last element or not. But the thing is, what if rather than storing this value at any position, when we find out that, suppose from this position we found out that yes, we are able to reach to this last position. So why do we need to check that whether we can reach to this last position or not? If at any point amongst these values, if we end up at this position, we would still be able to guarantee that we can reach the last element, because we have already checked this condition. So rather than checking for this whole thing, if we just check that, okay, from here if we can reach to this element or not, and if this is true, we can simply return true at that moment also. And let's see that in action. So let me clean this up a bit. Let's mark all the index values. Okay, initially we create an element called final, and this final element represents the last value in the given input, and initially we set it up to this index number 5, right? Now our aim is that at any point we found out that amongst these values, if anyone can reach this final element, then that element by itself becomes this final. So rather than storing all the values of at any given location, we are actually shrinking down our boundary of search. Initially the final is at this 5th position. Now we are at this 2nd position. So all we need to do is to check that whether our current index our current index and this current value, if sum of these two is actually greater than whatever final we have. So currently the final we have is this 5. So this is the final we have. Current sum of these two values becomes 4 plus 2 is equal to 6, which is greater than 5, which means that we can update the value of our final. So now this becomes our new final, and we basically don't care about this value anymore. Now we are at this 3rd location, and we try to see that the index plus its value. So this becomes 3 plus 0. Is it greater than our final? No, this is not greater than our final, because this is 3 and this is 4, which means that we can't do anything over here. So we drop this calculation and we check with the next element. So over here we have this 2 and we have the value 1. So 2 plus 1, is this greater than 4? So greater than final? No, this is also not true, which means we can't do anything over here. We again go back. Now this is 1 and this is 3. Now 1 plus 3, is this greater than or equal to value 4? Yes, this is greater. This is actually equal to 4, which means that we, from this point, we can come to this point. This is what this concludes, and which is what we want, right? So now we know this information, which means that we can update the value of our final again. So now the value of our final would become 1. So at this value, and now at this 0th position, we need to check that whether we can reach to this 1 or not. So over here the sum of these two value becomes 0 plus this is 2. So 2 is definitely greater than the final amount we have is 1, which means that we can reach over here. So the final element would be shifted to this point, and our at the end of our iteration the final would be 0. So now the final is 0. After the end of the iteration, we only need to check that what is the value of final. If final is 0, we return true. If final is anything other than 0, we return false. And this is a very good solution. The whole thing runs in the time complexity of big O of n. And if we see the space complexity, we are only storing one additional parameter. So we are essentially using constant space, and we are solving this problem. So this is a very efficient solution. Let's create a variable called final. Oh, it's Java, I can't use final. Let's call it final with an extra L, and we'll assign its value as nums.length -1. And now we will run a for loop, and we'll start it from I is equal to number of length nums.length -2, because we already know the result for the array length, and we will run it up until we reach to this 0th position. We'll do I minus minus, and inside the loop we are only going to check one condition, that if the current value of I plus nums of I, if they are greater than or equal to whatever the final value we have, we can update the value of this final parameter to whatever the ith value we have. And yeah, that should be pretty much it. Now we only need to check that if the value of this final character is 0 or not. So if it is equal to 0, we can return true, else we can will return false. Okay, let's try to run the code. Seems like our solution is working. Let's try to submit the code. Okay, our solution works 100% faster than all the other solutions. This is really good sign, and this is not constant time, but because we are basically shifting our boundary, we are essentially reducing the number of work we can do. And also, if you see the memory usage, we are actually better than 86% of all the other solutions. So this was a very small line of code, but this small line of code actually requires huge set of understanding. So see you in the next video. Thank you.